All right, so let me start a couple of minutes earlier by welcome you all to this to this parallel session of interacting dark matter. Thank you for your contributions to the talk. I'm sure it will be an exciting session. All talks will be recorded. As far as I know, there are no objections from today's session's speakers on this. They will be recorded in the cloud and then hopefully will be downloaded somehow. We will find out the way that we can download. Later on, we asked Gregory. So let me invite the first speaker, Professor Juan Garcia Bellido from Madrid, University Autónoma de Madrid, who is going to talk to us about primordial black holes as dark matter and entropic acceleration as dark energy. Please, Juan.
Thank you very much, Nick. It's a pleasure to be with you, and thank you for the invitation to all the organizers of the Marcel Grossman. It's an honor. Today, I'm going to describe two solutions, one for the nature of dark matter, the other for dark energy. So in the case of dark matter in terms of primordial black holes, and in the case of dark energy in terms of a new theory that we developed on entropic acceleration. The summary, I'll start with it so that at least you can grasp the basics before going through the talk, is that primordial black holes have become a hot topic since their detection by LIGO Virgo of the mergers of binary black holes, which essentially show that they are spinless and massive in the range of 1 to 100 solar masses. Their existence and their contribution to the dark matter budget is still uncertain. Okay, must become clear. For the moment, they are consistent with being 100% of dark matter, but there could be a combination of this and some other component. And this could be 100% only if clustered and white mass distributed. This is very clear. Uniformly distributed would not work. In the next few years, fortunately, the mass and the spin distribution of these black holes will be known from interferometers, laser interferometers like LIGO, Virgo, and CAGRA. In the future, by next generation 3G detectors like the Einstein telescope and possibly Cosmic Explorer. But not only this, also through microlensing surveys and by studying the clustering properties with the next generation of logical structure surveys. Now, the second part of the talk will be devoted to the present cosmic acceleration, and I'll show you how it can arise very naturally from relativistic entropic forces. The dynamics you will see is very similar to that of lambda cold dark matter, except that it has a prediction that the present rate of expansion is not 68 in agreement with the CMB, but actually slightly larger. So you all know about inflation generating large perturbations in special hypersurfaces. Quantum fluctuations of the fields during inflation generate ripples in space-time, and these are stretched to cosmological distances, and we can see them as tiny anisotropic variations in the sky in temperature and in galaxy distributions. Now, typically for models of inflation that have some dynamical field, you could have very large scales driving those fluctuations on the CMB, but on small scales, some peculiar features like a little plateau could generate a large amplitude of fluctuation, which later on, during the radiation era, will generate the collapse very copiously to produce black holes. And these black holes eventually become all of the dark matter. Now, this happens in the radiation era. This is important. It happens whenever a fluctuation is large enough that, through Penrose's theorem, primordial plasma cannot prevent collapse. And therefore, all the matter within the horizon collapses and form a black hole. Now, the distribution of those black holes is not uniform, like on the left image, but actually is more like the one on the right, because many different scales come at different times, and they correspond to different sizes of black holes. And these black holes encounter each other relatively near each other, and therefore can start forming clusters. It helps that typical dynamics generates non-Gaussian tails, and these induce a non-trivial clustering, which I won't have time to describe. So the picture in the right-hand side is, for the moment, perfectly consistent with observations. It comes in a broad range of masses. I'll describe what are those in a minute, and they come in clusters. So these masses are directly tied to the known thermal history of the universe. That is, what are the relativistic degrees of freedom, which from above the electroweak scale started to become non-relativistic, for instance, the top quark, the Higgs, the W and the C at the electroweak scale, at energies typically of 100 GeV, down to scales where quarks and gluons, which were relativistic, confined to form protons and neutrons, and then suddenly disappear from the relativistic plasma. They lower their pressure, the equation of state of the plasma dramatically drops, and this enhances the probability of collapse. There is no radiation pressure to prevent collapse, and therefore any fluctuation above a certain threshold will collapse to form a black hole. Eventually, pions annihilate, electrons and positrons annihilate, and all of these different scales that happen through the evolution of the universe, from 10 to the minus 10 seconds all the way to 10 to the 6 seconds, all of these happens providing a different mass spectrum, which could have masses of order 10 to the minus 5 solar masses, to a few solar masses, to hundreds of solar masses, to a million solar masses, depending on where you are and what particular epoch of the universe you are. Now, have we detected any of this? Well, it's very difficult to see the pristine, the primordial black holes. Typically, we observe black holes which have an accretion disk around them, typically those at the center of galaxies, and therefore it's very difficult to know which part of that black hole was actually primordial. However, very recently, with the detection of gravitational waves from the mergers of black holes, we have for the first time the ability to measure the intrinsic masses of those black holes as they find each other, create a binary, and finally merge through emission of gravitational waves. Now, the surprise was when the first detections of these through LIGO was that these masses were significantly above what you would expect from the usual astrophysical black holes that we observe in S-ray binaries, which we believe come from stellar evolution through the usual supernova explosions. These seem to have significantly higher masses. More importantly, even recently, some black holes have been found which had about 90 solar masses and more than 60 solar masses in the binary. And these masses do not agree with what you would expect from pulsating apparent stability supernovae. You would expect all of these black holes to not exist in nature, and they're there. So are they primordial? We don't know. Of course, there is another range that we know should not be astrophysical. That's if you find a black hole with a mass less than the Chandrasekhar limit. Simply from the Pauli exclusion principle, you don't expect through the degeneracy pressure to collapse a black hole with a mass less than 1.4 solar masses. So if we find a black hole of such a low mass, most likely it is primordial. And what are the evidences for this? Well, interestingly enough, it's not just gravitational waves and X-rays, what we look and radio, but we could also use microlensing. And there are these red dots in this figure superimposed on top of the gravitational wave emission, the detections of black holes. You see that these black holes have been observed with microlensing, and they go all the way to below a solar mass. So perhaps there is, in the halo of our galaxy, indeed, black holes of ranges from below solar mass to, say, tens of solar masses, which could be of primordial origin and seen only with microlensing and not with gravitational wave emission. Well, where do we stand at the moment? Recently, the LIGO Virgo and CAGRA collaboration have provided with the second catalog, GWTC2, with 50 or so binaries, hundreds of black holes, which together with those of Opal already give you a distribution of values of masses, which within a range of predictions which come. Sorry, can you mute, Diego, please?
I know how to make. Sorry.
Thank you.
Sorry.
So you have a prediction for what kind of mass spectrum should you expect. And fortunately, this is where you see most of the events that we observe with LIGO Virgo as well as with microlensing. Now, of course, these, I said at the beginning, they would come in clusters. So the rate of events that you would expect in these interferometers from the binaries which finally coalesce and merge is different from that of binaries in the uniformly distributed in the halo, and therefore one has to take into account the ability of those black holes to form clusters and merge and increase the probability of encountering and leave the cluster and finally merge outside. And this does play a role. In particular, if you ask what is the merger rate and how does that compare with the observed events in GWTC2, you see that the events that have called attention, they were discovered and made special events like 1905-21 or 1908-14, and the recent so-called neutron star black hole binaries, but actually most probably primordial black hole binaries, they all lie in regions where you would expect according to this scenario that we proposed. In the future, of course, by knowing the spin of those black holes, we might have some hint as to their primordial origin. Why? Because a primordial black hole, simply because it's the collapse of the horizon which provides the initial black hole, and essentially the whole black hole horizon is essentially the same size as the causal horizon. You see that there is no moment conservation of angular momentum, which may impinge on a final spin, and therefore you expect all the black holes, primordial black holes, to be spinless. However, there are evidences from LIGO, Virgo, and Cagra that essentially all the spins are clustered around zero spin for both the effective projection of the spin towards the angular momentum, as well as the final spin of the binary. But most interestingly, recently we analyzed the possibility that if you are in dense clusters, it might happen that one of those black holes scatter off each other, producing a lengthening or frame dragging effect, which would induce a spinning of the massive black hole. We've studied how that happens with equal masses, so Q equals 1, or very large mass ratios. And we observed that it is possible to increase the spin of those black holes, even if they started at 0 spin, and acquire some order 0.2 or even up to 0.5 in dimensionless units for the spin before they finally merge. And I think this is extremely interesting and might be a clue for us to search for. In the future, clearly, the Einstein telescope will play a fundamental role in the detection of these black holes. It would have tremendously better sensitivity compared to the present detectors. It has been approved by the European Strategy for Future Infrastructures roadmap, and we are looking ahead of the construction and design of this new tool that we'll have in Europe. This will allow us to reach redshift 100. That means we'll be able, with the Einstein telescope, to touch upon the really primordial origin of these black holes. So if we keep on seeing black holes all the way to 100, that means they could not have come from stellar evolution. Now, let me move now the rest of this few minutes that I have into the second part of the talk. And this is a radical change. What we have proposed here is to incorporate into a generally covariant formalism the non-equilibrium thermodynamics that we know happens in certain occasions in the expansion of the universe and in certain locations, particularly in gravitational collapse in our universe. So up until now, those features, those out of equilibrium thermodynamic phenomena could not be incorporated because of the differences in the way they treat time. General relativity is time reversal invariant, while non-equilibrium thermodynamics has an arrow of time. So incorporating this into a variational principle gets some efforts. We managed to incorporate this as a variational constraint. This second law of thermodynamics is a variational constraint on the evolution equations, the Lagrangian formulation of general relativity, and obtain a modification of the Einstein equations by adding a new term, what we call the entropic force term. Notice that through Bianchi identities, general covariance of the theory, we know that the non-conservation of the energy momentum tensor must be directly linked or tied to the covariant derivative of these entropic forces, and you will see that this will play a role in both the gravitational collapse and the expansion of the universe. In order to incorporate this difference in time, we go explicitly to a 3+1 splitting of space-time, the ADM formalism, and our lead derivatives along the normal vector to equal time hypersurfaces will be a generalization of the time derivative. Therefore, we can construct an extrinsic curvature, and we can incorporate the far from equilibrium condition as a constraint, as you can see here, from the Lagrangian variation of the Lagrangian with respect to the entropy, which is one of the quantities on which the Lagrangian matter Lagrangian depends on, and a force projected on that hypersurface. The Hamilton equations are modified by these extra force in the variation of the canonical conjugate momentum to Hij, and also in the Hamiltonian constraint. The Hamilton constraint, you will have extra terms coming from these entropic forces. Now, a very natural way to understand the effect that these entropic forces have on the motion of particles is by looking at the congruence of geodesics or world lines in general. They don't have to be geodesic, there could be some acceleration. And we are familiar with this formalism, which would give rise to the Rachaduri equation, the second equation, by splitting this congruence of geodesics into the trace, the symmetric and the antisymmetric part. This provides the Rachaduri equation where two of the terms, sigma mu squared and theta squared, are positive. And in case we choose the normal to be orthogonal to the hypersurface, then we know the vorticity vanishes. And using the modified Einstein equations, where we incorporate this extra force term, even for strong energy conditions satisfied, that is, when this is satisfied, you find that it is possible to generate an acceleration. At least if you have a sufficiently large and positive entropic contribution, you could avoid recollapse. So you could have a congruence of geodesics which expands, eventually gets halts and recollapses. This is what the Penrose theorem would say. You would form a singularity, you would form a black hole in the horizon, but if you have sufficiently large entropic forces, it could expand forever. We will see that this will play a role for understanding our present acceleration of the universe. So let us apply all this formalism to the homogeneous and isotropic universe, Freeman-Lemaitre for Bertrand Walker, with this line element. Take a homogeneous and isotropic energy momentum fluid, take into account the non-conservation of the energy momentum tensor, and notice that the second law of thermodynamics very naturally generates a generalization of the usual equation. Instead of 0, you have here T times S dot. That means that in most of the cases where you would have in the expansion of the universe a perfectly adiabatic expansion, so sufficiently fast microphysics, keeping some local thermal equilibrium, that term would be 0. Most of the radiation would expand as usual, matter would expand as usual. It's only certain components, we will see which ones, will play a role by inducing an extra term. And it's interesting, if you take the Hamiltonian constraint and take derivatives and use the second law of thermodynamics, you find an extra force, just like in the Rachaduri equation, which contains this extra positive term, as long as there is growth of entropy. So a growth of entropy may play the role of an acceleration, which is creates a repulsive force compared to the always positive ordinary matter contribution, which tend to make the expansion go slower and slower. So the specific model that we used was a causal horizon, which satisfied this property, Ts over A is proportional to sinh, it's inversely proportional to G, and it only depends on omega curvature if you want in this quantity x naught. That depends on the number of e-folds, reheating temperature, and so on. So if you now take the Hamiltonian constraint and you write it in conformal time, you see the usual terms, the well-known matter and curvature terms, and instead of a cosmological constant, here we have a time-dependent term. This term will grow from 0 and very slowly, with a sinh, will very quickly accelerate the universe. So if you compare with the standard lambda cold dark matter at high redshifts, you don't see any difference. Essentially, in say CMB, it behaves exactly like lambda cold dark matter. As we approach the region where you start feeling the presence of this accelerating force, this repulsive entropic force, then you enter into a caustic point. You have a minimum co-moving horizon, and this grows to become larger than 1 today. So you could ask, at what time will that happen? Okay,
sorry, you have 3 minutes.
Very similar, 3 minutes. Yes. Yeah. Actually, this is the one before last. Thank you, Nick.
Oh, perfect.
In lambda cold dark matter, the caustic point is at 0.65 in redshift. Here is at 0.83. But most interestingly, I would say the interest of this model is that contrary to lambda cold dark matter, there is no vacuum energy. We don't have a rate of expansion approaching a constant value at infinity. It decreases. It has a value larger than the one expected from lambda cold dark matter extrapolated from the CMB. Actually, you could take the numbers so that this becomes 0.74, like what we have learned from the H0 tension. But eventually, beyond the scale factor 1, so in the future, this component will itself dilute. The energy density goes like 1 over AQ, Ts over AQ, and this will dilute, and eventually you will end up in Minkowski. You're not ending up in de Sitter, as you could see in this figure, right here. Square pluses is the sitter. Sorry, it's Minkowski. Now, you could ask, well, how can we distinguish this from standard measurements with the CMB and with large-scale structure? Fortunately, the deviations from lambda cold dark matter is not significant. We have an equation of state which you can expand in terms of the scale factor. So today, this would be like minus 0.941, perfectly within errors, and a derivative of about 0.3, again, within errors. We are doing now a careful analysis with all the data. But I want to end with this notion that up until scale factor 1, there is no real difference with respect to lambda cold dark matter. It's only in the future that we'll see the difference. And with this, I conclude. Let me describe first the first part of the talk. Thermal history predicts that primordial black holes should appear with a multimodal mass distribution, 10 to the minus 5, 100, and 10 to the 5 solar masses. Possibly, we could even go down to 10 to the minus 10 solar masses if there is new physics beyond the standard model. The predicted spin and mass distribution of primordial black holes have already been measured with LIGO Virgo and OGLE. They span a range between 1 and 100 solar masses. We are searching for below solar mass black hole also in the data. Fortunately, it's possible within the next few months or perhaps years. With round 4, we might detect those below solar mass black holes and finally convince ourselves that primordial black holes exist. This would be a tremendous paradigm shift for structural formation of the universe. Moreover, on the second part of the talk, I described how entropic forces appear when you incorporate non-equilibrium phenomena in a general covariant formulation of general relativity. When you do the 3+1 slicing of ADM, you find that gravitational collapse follows a modified Ratchaburi equation, and we can have you can prevent collapse or recollapse from a congruence of geodesics. This affects the description of cosmic acceleration in our universe. Notice that we don't require any inclusion of any other matter content. We don't need a cosmological constant. We don't need any other modification of gravity. Just first principles, thermodynamics, general relativity, and quantum mechanics provides the ingredients that we need in order to explain the present acceleration. And with this, I finish. Thank you very much for your attention. I'm open to questions.
Thank you very much for this very nice talk. So we have time for questions. Now let me see the order. I've seen Carlos and Dodi. Let me see the order. I think Carlos is first, please.
Okay, hello. Okay,
Hi,
thank you very much
Welcome.
for the talk, very interesting. So I have one basic question about primordial black holes. When you mentioned the possibility due to this multimodal mass distribution to have values up to what 10 to 3, 10 to 4, 10 to 5. These values is necessary to have a cluster of seeds primordial black hole to then clamp into these large values, or directly you can end up with those?
It's a good question. Now, if you follow the same reasoning that we had for the collapse at the QCD epoch, that is the reduction in the number of relativistic degrees of freedom, which then lowers the equation of state, as you can see here on the left-hand side, in the evolution in time or in temperature, then you see that at that time, as long as the amplitude of fluctuation is sufficiently large, the whole horizon, which in the case of E plus E minus annihilation corresponds to 10 to the 6 solar masses, the whole horizon would collapse to form a black hole. Now, 10 to the 6, it's a very natural seed for producing the supermassive black holes that we observe in our galaxy and in other galaxies, N87, and all the galaxies all the way up to 10 to the 12 or so solar masses. Now, those black holes of such a high mass probably come from the accretion of matter from accretion disks that rotate around those black holes, which acted as seeds. So I would argue that rather than waiting for black holes to form sufficiently large through mergers or accretion through the age of the universe, which is difficult, here you would have seeds to structures. So galaxies would start forming around those black holes. They would be the seeds onto which gas would accrete and start forming the first galaxies. So it's very interesting because you could start to search for this with the Einstein telescope, which can reach redshift 1000, and see whether those mergers and phenomena and like accretion leave an imprint on our detectors. So there's an opportunity that up until now
we have to be, the answer should be shorter, unfortunately. So
I'm sorry.
No problem. Dodi, can you unmute then, please?
Okay, thank you.
Yeah, so I just thought that the first half of your talk and the second half seemed a bit disjointed. So in the first half, you've got inflation, right? And you have this feature in the spectrum, and that gives you primordial black holes. But then in the second talk, you're throwing out vacuum energy, you're throwing out scalar fields.
But you still have inflation.
If you've got a scalar inflation, why not have one for dark energy? Right. Yeah. So why not have? I mean, okay. What makes the scalar field be minimized at 0 and no cosmological constant in the second half?
It's a very good question. So we don't solve the cosmological constant problem. We just assume there's a fundamental principle which tells you that vacuum energy does not gravitate. Only gradients create forces. So here we have gradients of entropy. In other forces, we have gradients of fields. In inflation, we have gradients of fields providing acceleration. So what I'm saying that vacuum energy doesn't play a role in terms of acceleration. Somehow that doesn't gravitate. We don't know what is the fundamental quantum gravity principle which drives that conclusion. The things that something which is extremely difficult at the present, which is to agree on introducing a cosmological constant and at the same time argue that it has to be very tiny, 120 orders of magnitude, is directly thrown out of the window because you don't need such a cosmological constant.
Okay, sorry, I have to cut it short now. I'm sorry
about
it's
that.
a very interesting discussion myself. Tomorrow we will have more time. So let's thank the speaker again once more time.
Thank you.
And let me pass, not at all, I'm sorry that I have this tight schedule.
I'll talk to you tomorrow.
Yeah, absolutely. But please, now I would like to invite Dodi Marsh, who's going to talk to us about fuzzy dark matter.
Yeah, okay, great. Thanks, Nick, for the invitation to speak in this parallel session. And I'm going to tell you all about fuzzy dark matter. So, first of all, I've got to explain just a little bit of the physics. I'm going to spend most of my time on phenomenology. Okay, but the first thing is fuzzy dark matter. I'm going to be talking about is a scalar field which is formed from vacuum realignment in the same way that axion dark matter is. It's just a more general term. Okay, so a scalar condensate evolves according to the Klein-Gordon equation, and where Hubble acts as a friction. When the Hubble constant is much, much larger than the mass, this is overdamped, and the field essentially remains wherever you start it. And that means that at early times, such a fuzzy dark matter model has an equation of state similar to dark energy. So it's equation of state -1. Then the Hubble constant falls over time, and when the Hubble constant drops below the mass, the field begins to oscillate, and an oscillating scalar field has the equation of state just like matter, which you can prove by a WKB approximation. So that's where you get your dark matter relic density from that initial displacement. Now, if you argue that that initial displacement should be fixed by some scale that you know from elsewhere, and you fix that displacement to be, say, the Gut scale, then you get the following prediction for the cosmic density in, I'm using A here because it's an axiomatic particle, that for the cosmic density in this particle as a function of the mass. And I'm kind of varying the Gut scale over about an order of magnitude, and you get this hockey-shaped thing, and you get the right amount of dark matter for masses around 10 to the -22 to 10 to the -18 or so electron volts if you fix the initial displacement at the Gut scale. If you have to keep that displacement at the Gut scale, heavier particles will overclose the universe. But you can always just lower the initial scale if that's what you want to do. But similarly, you predict that there would be if there were many such particles, which you might expect in string theory from light axions like moduli, you predict that the lighter particles make up a subdominant population of fields which you can search for. Fuzzy dark matter, as well as differing from thermally produced dark matter by its equation of state, as I just showed, it also differs in its dynamics in that it has a gene scale, has an effective pressure, and this was something pointed out by Klopov and Zordovich in 1985. So you consider that the equation of state for the field perturbations and reduce them to an effective fluid in the WKB approximation, and this is how the overdensities evolve. And the gradient energy in the Klein-Gordon equation leads to an effective sound speed. So then we have two terms in this evolution equation. We have gravity here just in the Newtonian limit, which gives rise to growth of fluctuations, and pressure, which opposes them. And this leads to a gene scale where these two are equal. And it means that large K fluctuations, small wavelengths, don't grow, they oscillate. And the gene scale is an interesting scale, about 9 inverse megaparsecs, for masses around 10 to the -22 eV. And that's how we can probe these kinds of masses using cosmological observables. The next bit of physics where fuzzy dark matter differs from standard cold dark matter is inside galaxies. So it is fundamentally different in this case from other dark matter candidates. Warm dark matter is self-interacting dark matter. Now what we do is we take the non-relativistic limit of the Klein-Gordon-Einstein system, and we arrive at a Schrodinger-Poisson system. So psi is sometimes called the wave function. It's not a wave function. This is a nonlinear Schrodinger equation. So you have the square of psi is basically the dark matter density, and it's driven by the Newtonian potential phi, which is itself determined nonlinearly by the Poisson equation. This is a challenging equation to simulate because there are a wide variety of scales. There's the scale at which there's the de Broglie wavelength, which is say a kiloparsec, but we're forming structure across the whole visible universe on gigaparsec scales. So, and the overdensities in the field cover a range of at least 10 to the 5 from the background to the galaxies. The physics that appears as different here is the gradient pressure, just like in the linear regime for the gene scale. And these give rise to stable boson stars on the smallest scales, undergo interference, and also have fluctuations within them. What does this look like inside a galaxy? So hopefully you can see this movie. And this is a movie taken from a simulation by Jan Veltmat at Göttingen. So this is the inside of a galaxy made of fuzzy dark matter. This rotation now is just the camera rotating. And you see in the outside of the dark matter halo. And these fluctuating granules lead to heating and cooling. So if I have stars or gas within that dark matter halo, then these fluctuating granules can be modeled as quasi-particles which perturb the distribution of stars and gas. The quasi-particle mass is basically the local dark matter density times the cube of the de Broglie wavelength. And these quasi-particles interact with, say, the stars or the gas in your galaxy, and they lead to two-body relaxation. And this is something that you can just look up in Binney and Tremaine, and you can estimate the relaxation time caused by these quasi-particles. And there's a transition where tracer particles of certain mass are cooled, right, whereas others are heated. And it's on this time scale, the relaxation time, that the halos don't behave like standard cold dark matter halos. Okay, so that's enough of the physics, and I can now get on to tell you about the phenomenology of fuzzy dark matter and some cosmological constraints on the mass and density. So I'm first of all going to talk about the cosmological background power spectrum, the cosmologist's gold standard. So here is the CMB. All the features in the CMB are predicted from linear perturbations of sound waves in the plasma. And I'll remind you that large angular scales to the left of the first acoustic peak probe the expansion rate in the late universe and the distance to the CMB and essentially dark energy like phenomena. Whereas the smaller angular scales probe the expansion rate in the radiation dominated era and through the diffusion damping or silk damping scale, which depends on the expansion rate. And so if you include fuzzy dark matter rather than cold dark matter, it has this transition in the equation of state from -1 to 0. And this changes the expansion rate compared to lambda CDM in both of those epochs, depending on the particle mass. And so here I'm showing the CMB power spectrum on a slightly different scaling on the y-axis in the previous figure, but here's the first acoustic peak and lambda CDM in black. And then if I introduce very light fuzzy dark matter, and here with an enhanced density, so you can see the effect by eye, you see that these light fields, 10 to the minus 27 electron volts, 10 to the minus 26, even 10 to the minus 25 in the residuals plot, differ from standard cold dark matter in their predictions for the CMB. And thus we can constrain the density, the allowed density fraction and mass of such particles. And here are what the constraints look like in a summary plot. So the CMB anisotropies constrain their lightest region from about 10 to the minus 24 to about 10 to the minus 33 electron volts to be a subdominant fraction of the energy density of the universe. And that bound is about 2.5%. It also gives you an absolute lower bound on the dark matter particle mass. If the dark matter is lighter than 10 to the minus 24 electron volts, it is not consistent with the CMB. And this is a very rigorous bound because the physics is all linear and the data are very precise. That bound can be improved. You might want to wonder, can we reach the prediction for where we expect to be from the gut scale, which is the hockey puck shaped thing? Using CMB stage 4, for example, at the Simons Observatory, you can improve the bounds by quite a lot, but you can't get into this region. So the question then is, what other probes can we add on top of the CMB to try and move over into the predicted region from a gut scale, from a gut fundamental scale? One of the things that we can add in the cosmologist arsenal is galaxy clustering. In this case, this is work done by a PhD student, Alex Legay, at Toronto, on the baryon oscillation spectroscopic survey galaxy clustering. So what Alex did is he simulated the galaxy bias, and he simulated Boss mock catalogs using an approach called peak patch for cold dark matter and cold dark matter plus axioms plus fuzzy dark matter. And when you model the bias correctly, you find that even though there is a gene scale, the fuzzy dark matter actually increases the galaxy power on large scales due to bias. You've basically got the same number of galaxies, but you have to stick them into fewer dark matter halos. So then you see here on the left-hand side, the simulated spectrum, and the case where you add in a fraction of fuzzy dark matter, you actually bias the power spectrum high relative to the case of CDM alone. So then when you combine in the right-hand plot cosmic microwave background constraints, which are in gray, versus combining with galaxy clustering, which are shown in red, you gain an improved limit on the fraction omega A over omega D of fuzzy dark matter across this range of masses I showed before for the CMB. You gain an improved constraint by about a factor of 3 using just existing data, but combining the galaxy clustering and CMB data. Another bit of data that we've got lying around, essentially, as theoretical cosmologists, is cosmic shear. So here I'm using DES dark energy survey year 1 cosmic shear, and this is work that a postdoc I've been working with, Mona Dentler, has done and is forthcoming very imminently. We now want to go into nonlinear scales, so we adopt a halo model for the power spectrum, and we marginalize various nuisance parameters in that halo model. And so here I'm showing one of this cosmic shear observables, the psi plus correlation function, as a function of angular scale for different fuzzy dark matter masses. And I'm going from 10 to the minus 25 electron volts to 10 to the minus 22 electron volts. And at about 10 to the minus 22, you would be indistinguishable from cold dark matter. But the other cases all differ. But again, it's not a simple trend. There's an increase in power over some scales caused by the transition from the quasi-linear to the fully non-linear regime. As I say, we marginalize over parameters counting for that. This gives you an increased lower bound on the dark matter particle mass to about 10 to the minus 23 electron volts. Looking forward to the future, the future of all cosmology, right, is intensity mapping. So here for neutral hydrogen intensity mapping at redshifts below the epoch of reionization. This is work that I did with a master's student, Eric Bauer. So a similar biasing effect as we saw in the galaxy power spectrum happens for neutral hydrogen. And again, we use the halo model. And we forecast what the square kilometer array could do. And so the biasing effect is shown on the right-hand side. The power spectrum is increased when we have a fraction of fuzzy dark matter relative to cold dark matter. And on the right-hand side, you see the forecast for what you can do with the square kilometer array. So the black line is the forecast CMB constraint with the Simons Observatory. And then the colored lines are what you could do with SKA. And these are finally eating into the predicted region from the gut scale initial displacement, and also testing the 10 to the minus 22 electron volt range. And also here, we're in addition also marginalizing over nuisance parameters of the halo model, in this case to do with astrophysical foregrounds. Okay, there's 2 more constraints that I want to try and tell you about in the next 5 minutes. And the next one is superradiance, black hole superradiance. This is very powerful. This very powerful probe. It depends only on the mass, not on the background density of the fuzzy dark matter. So in this case, you have Kerr spacetime, and on Kerr spacetime, the effective potential for the scalar field has a barrier, both going in and out. And this means that the quantum fluctuations on this background can be amplified by the Penrose process. And where does the energy come from? The energy comes from extracting spin from the black hole. And this means that if you think of a range of black hole masses and spins, certain spins and certain masses are spun down by the presence of a background scalar field and reduce the expected spin of black holes. And then that means if you observe black holes with a certain mass and a high spin, that is not consistent with the existence of a bosonic field that is resonant with the horizon size of that black hole, essentially. So here's what this would look like. So this was work done by a PhD student, Matt Stott, who was at King's. And so what he's showing here is the black hole Reggie plane, mass and spins, and the region that is excluded for a boson of a certain mass, and then data from various black holes. And you see that some of them have measured high spins, in this case LMC-X1 and M33X7. And if the excluded region passes over that range where you know black holes exist, then you can exclude particles of that mass. And that's shown in the right-hand plot, the exclusion probability of a particle of a certain mass. And this becomes large when the region that is excluded by superradiance overlaps the observables. So if you do that for all known black hole masses and spins, then you exclude two bands of fuzzy dark matter parameter space. One around 10 to the minus 10 electron volts from the stellar mass black holes, and one around 10 to the minus 18 electron volts from the supermassive black holes. And this is independent of the cosmic density. There's an interesting gap here, which I call the 1 Hertz axiom, so around 10 to the minus 15 electron volts, 1 Hertz oscillation frequency. And this is inaccessible because intermediate mass black holes have not been observed. However, if they exist, then their gravitational wave signals will be observable by LISA in the in-spiral phase, and you could potentially exclude this regime. But I think it's a very interesting region to think about, because it's not currently excluded, and it's something that we can also probe experimentally using the neutron electric dipole moment, and also using nuclear magnetic resonance in experiments like Cusp.
You have 3 minutes. 3 minutes.
Thanks. Finally, with superradiance, something really interesting you can do, which a postdoc I've been working with, Firas Mehta, has looked at, which is that you can probe the topologies of compact dimensions. So if you have a compact space like a Calabi-Yau, you predict many axion fields. We can derive their mass spectra, and we can derive their mass spectra assuming certain facts about modular stabilization, and we're able to exclude certain fractions of our 200,000 string theory compactifications with a certain range of Hodge numbers. So you can exclude about 50% of this database of string theory compactifications up to Hodge numbers of nearly 200. Okay, last 2 minutes, fuzzy dark matter and galaxy formation. How do you probe this window here from 10 to the minus 24 to 10 to the minus 19 electron volts? Well, first of all, you can look at the distribution of high redshift galaxies, here the Hubble Ultra Deep Field, and you can ask what's the lowest mass halo at the highest redshift that Hubble sees. Certain halos are excluded by that gene scale that I talked about before. Low mass halos don't form in fuzzy dark matter, and they also form later at lower redshifts. When you look at the Hubble data and you do this, you gain a bound on the fuzzy dark matter mass of about 10 to the minus 22 electron volts, which you'll be familiar with if you've looked into this subject before. So, and Lyman-Alpha Forest power spectrum can improve this even more, up to 2 times 10 to the minus 20 electron volts. Very interesting work recently by Keir Rogers. And if you improve that with the open region here, but say assuming some increased errors with W first, you can also eat into this predicted region from the gut scale. The last thing that you can use to probe fuzzy dark matter is Eridanus 2. This is a very low mass galaxy, ultra faint dwarf galaxy orbiting the Milky Way. Here's where the fluctuation timescale comes in. The stars in this low mass galaxy would be kicked out by that fluctuating fuzzy dark matter halo. In the diffusion approximation, you can work out what the time-dependent potential would do to a distribution of stars. And it turns out that this quasi-particle heating excludes a range of fuzzy dark matter masses well between 10 to the minus 20 and 10 to the minus 19 electron volts. There is a gap between about 10 to the minus 22 and about 10 to the minus 20 where this approximation that we use, this is work I did with Jens Niemeyer, starts to break down. So you might ask, is there a fuzzy dark matter window available that is not probed, say, can you get around Lyman-Alpha Forest, that's allowed by the high redshift universe and is not excluded by Eridanus 2? And there is one possibility to do that, which was looked at by Siyu Shive and his collaborators, which is that if Eridanus 2 is in a halo that is very, very massive, much more massive than many of the other satellites of the Milky Way, but that halo was tidally disrupted by the Milky Way, then the atmosphere of the halo, those fluctuating quasi-particles are taken away. And you end up with just a lone soliton boson star in the center. That would have no fluctuations and the star cluster could survive. So that's all I wanted to tell you. Lots of constraints on fuzzy dark matter. There's a range of around 1 Hertz that might survive. And maybe you can survive around 10 to the minus 22 electron volts. So thanks very much.
Thank you very much for this very nice and interesting talk and work. We have time for a couple of questions. Yes, Carlos?
Yes, hello, David. Thanks for the talk, for all the updates of fuzzy dark matter. So I want to know if you can comment about how it stands, fuzzy dark matter theory, at least in this simple Schrödinger-Poisson, respect to the dark matter surface density relation, meaning when you go to different galaxy types, how it stands the relation of size and masses of these fuzzy dark matter halos, and also in terms of the particle mass.
Yeah, so there's so I think you're talking about things like the Tully-Fisher relation. That is not predicted so far. So far by these models. The scaling, for example, between soliton to galaxy mass, you can't explain those scalings using solitons.
Yeah.
However, if the particle is heavy enough, then it behaves just like cold dark matter. And anything that cold dark matter predicts, fuzzy dark matter would also predict, as long as the scales that you're talking about aren't affected by the wavelength of the particle. So I would expect that at high enough mass, if CDM does it, fuzzy dark matter does it.
Okay, so we maybe say that this attention for this model of fuzzy dark matter, simple fuzzy dark matter, or not necessarily, you say, respect to these observables?
Well, I just don't know if the right simulations have been done, to be honest.
Okay.
Yeah, I don't know if the right simulations have been done. You'd have to say that maybe there could be a region where the baryonic feedback that works for cold dark matter does not work for fuzzy dark matter. If the fuzzy dark matter heating works against the baryonic feedback, it is possible that happens, but I don't know that anyone knows.
Yeah.
Really.
Okay.
But once you're heavy enough, everything looks like cold dark matter, and it should work fine.
Thank you.
But yeah, maybe there's a light regime where it doesn't.
Okay, thank you very much again, the speaker, for this nice talk. And let me now invite Carlos Arguelles, who is going to talk to us about dark matter halos from an entropic principle and its link to particle physics. Carlos, you're muted, I think. Carlos?
Yeah.
Ah, okay, good.
Yeah, sorry, I was muted.
That's right, yes. I'm sorry, I have to mute everybody and people forget to.
No, sure. Okay,
Okay.
I want to thank Nick and the organizers for this nice meeting and, well, all this parallelization on dark matter. Well, yeah, I talk about dark matter halos from maximum entropy principle and linked to particle physics. This talk is mainly based on the works here that I show here in collaboration with the people from ICRANet, Rupini, Jorge, well, also Nick from King's College, Andreas and Eduardo Becerra, and, well, my students, Rafael and Manuel. Okay. Yeah, so we'll go fast outline of the presentation. I will talk about dark matter halo formation from entropy maximization in the case of fermions. Then how you can reach stability and a lifetime of this gravitating system of fermions in cosmology. Then I will show how it can be obtained a supermassive black hole formation scenario out of the profiles of dark matter obtained from this maximization principle. Then application to Milky Way. And I have time, I will talk about the universality of these profiles and possibility to model these neutral fermions as neutrinos. Okay, so let's start with some preliminarities about how dark matter halo can be formed from starting from the known Blasov-Poisson equation. You have here F as the fine-grained phase space density, and coupled with Poisson equation here, and proportional to the mass density of the particle. So this starting from this Blasov-Poisson, you can divide the phase space density into an average and coarse graining plus fine grained fluctuations tilde. And once you introduce this separation here, you obtain this coarse graining version of this Blasov-Poisson equation, where you can separate a so-called diffusion current to the right-hand side, and you have a kind of a in the left-hand term as similar to the Blasov equation of coarse graining, and in the right-hand side the diffusion current, which is in terms of the average of the fine grain fluctuation. So interestingly, out of this convection diffusion equation, you can impose the first and second law of thermodynamics, so conservation of energy and maximization of entropy, of course there is entropy, and well, this was shown very nicely by Pierre-Henri Chavany in 1998, that out of this maximization entropy principle, during the evolution of the system, maximizes rates of entropy creation while satisfying the constraint fulfilled by the dynamics. And so if you apply this maximum entropy principle that I showed before, together with quasi-linear theory, you can write the above equation at coarse grain level to this modified Landau equation, like this, and find a possible stationary solution of this coarse grain distribution function at relaxation. And it can be shown that when the diffusion current is said to be constant, for example, you have a diffusion of particles outside the system at constant rate, you can demonstrate that there is a solution which is of Fermi-Dirac type. And probably you recall this as it resembles the famous or the original Lynden-Bell violent relaxation, what we have shown in the 60s, late 60s from an heuristic approach. But in this paper, this was nicely demonstrated from a more rigorous approach from a kinetic theory. So, well, of course, this kind of approach were originally developed for classical particles, but interestingly was extended this mechanism for neutrinos, so for distinguishable particles, for example, neutrinos, a couple of decades after Lynden-Bell work. And for example, in the case of fermions, more generally, the maximum accessible value, this eta zero of the phase space, is fixed by Pauli principle. And of course, it goes as proportional to the mass to the fourth inverse to the H Planck cube. So now, once we have a most likely coarse grain phase space density at relaxation for fermions, you can ask if under cell gravity, I mean, you can show, it was shown in the late 60s, that fermions under cell gravity do admit a perfect fluid approximation, and therefore it is possible to solve the Einstein equations of for semi-degenerate gas of fermions in hydrostatic equilibrium, so the TOV equations. So I will write these equations in this dimensionless form, even if they look a bit weird. Just let's recall that the second equation is the so-called TOV. First is, of course, mass equation, and then we have also Klein and Tolman, zero and first law of thermodynamics for these relaxed systems and energy conservation. And the source of these equations, pressure and density, are given by the parametric equation of a state, which can be written in terms of the Fermi-Dirac phase space distribution function, which has this cutoff in the energy of the particle. So, which I showed you before, this has to be considered coarse grain level, as I showed before. And this cutoff is because for energies of the particle less than the cutoff energy or escape energy, you have the system, the particles inside the system, and for energies larger than that, there is a particle escape and there is no more particles. So This distribution function is truncated in energy, and this is the energies we will put as a relativistic energy, meaning that depending on the momentum, it can be either non-relativistic, but also can include more relativistic degrees of freedom. Okay, so you have this Einstein equation for stationary fermions, set gravity, and you have to, this is a rather complex boundary condition problem. You have to solve for the mass, the central degeneracy, theta, which is chemical potential over kappa T, the temperature parameter beta, and the W, which is the escape energy. So you have 4 free parameters: particle mass, temperature, degeneracy, and cutoff. And you have to give 4 given condition at the center of the configuration, right? It's a boundary condition problem. Interestingly, the most general solution out of this boundary condition problem, when you put the boundary condition at the border of the configuration, typically for spiral galaxies, so you have to fill with a mass of 10 to 11 solar masses at a radius about tens of kiloparsec. You can know the most general profile out of this solution is this core halo shape, where the core resembles Pauli principle, but with self-gravity. And then you have a continuous transition to Boltzmannian distribution. So while the core is support against gravity by degeneracy pressure, the halo part, the surrounding atmosphere of fermions, are supported gravity by thermal pressure. So these solutions are specific of positive central degeneracy, typically for values larger than 10, but in this case it's 30. And this, for example, this typical profile, you can see that matches typically density profiles of INASTO or NFW at scales where observations allows, but at the center they develop this central core, which depends, interestingly, on the particle mass. And we will see later on what we can do with that. So, well, I have just shown this, the central core fulfills the quantum condition. So the thermal de Broglie wavelength is larger than the particle mean distance. And well, now let's talk about a bit about the stability. So these profiles, whether are interesting, you can wonder how a self-gravitating system of this fermion reached the steady state, because I've shown you before, we have built a stationary system, but it would be nice to show how it can reach this steady state. So to find a dynamically and thermodynamically stable configuration of fermions in general relativity, we need to find solutions that maximize the global entropy. So it's an integral of the Gibbs-Duhem relation for entropy density. And instead of doing the second order variation of entropy in order to find stability, we will apply the so-called Cusp criterion, which you can analyze the stability without calculating the second order variation of entropy, but just build a caloric curve and checking the derivatives of this caloric curve, meaning energy versus inverse of temperature. Series of equilibrium was developed for the first time for halo size, for configuration of halo sizes for masses above 10 to 10 solar masses recently. And the caloric curves show this nice profile, which resembles the hydrothermal catastrophic feature of Boltzmannian systems, but in this case, due to fermionic or Pauli principle, this spiral unravels, and then you have a branch of stability here. This I will not explain in detail, but depending on how you enter this curve, if you go clockwise and then anti-clockwise, you can gain degrees of stability or instability. The point is that in these blue lines are stable, while these dashed lines are unstable. I will show now how do we obtain realistic dark matter halo in cosmology via this method, and therefore one should ideally calculate first the power spectrum in a given, let's say, warm dark matter cosmology of KV fermions, KV particles. Well, then we have applied the pressure formalism to obtain a typical virial mass, a given virial redshift, introducing the mass variance, and it depends on the critical over density, to find the typical virialized mass. And for example, yeah, for the black is cold dark matter, but and the red and pink are warm dark matter. For example, for a particle mass of let's say 48 keV, you find this mass scale of 10 to 10 at this typical radius, which is tens of kiloparsec. And once you pick this value, calculated from the power spectrum, and then to apply a Preschechter, you use as a boundary condition to find all the families of stable solutions across the caloric curve, sorry, that I show here. And the energy is this dashed line here is the specific energy needed corresponding, sorry, to that mass of 10 to 10. And as you can see, there are 3 possible solutions, 1, 2, and 3, well, and then 4 here. And interestingly, among all the possible solutions, only solution 1 and 3 are stable, dynamically and thermodynamically. But interestingly, the solution 3 is a core halo shape and has the right plateau densities and 1 halo scaling radii in order to fit the spiral galaxy's halos. So interestingly, it can be shown that starting from a Fermi in the early universe, you can end up with a visualized object to then show to relax and to these core halo profiles being stable, and then you can show that it's also long-lived, very long-lived. This is a feature of thermodynamics of relativity systems. Well, you end up, what I didn't say, it's a bit specific, is that in this second branch of stability, the solutions are local maximum of entropy, and then they can remain frozen in a very long-lived state. This is typically of thermodynamics of segregating fermions. And well, so you can have this kind of profiles. I will jump this about criticality, and let me go to the Milky Way application. So now, what if we apply this theory to the Milky Way? Well, we know Milky Way has a disk, bulge, central object, and rotation curve. But let's take a look inside about the central star cluster. We know that around Sagittarius there is a cluster of S stars, which goes from milliparsec or a bit below up to the parsec. And from the observation of S2 star, one of the closest to the galaxy center, it was possible to constrain the central object mass to 4 million solar masses, and we have seen the last Nobel Prize of last year on that. And now the question is, can these core halo profiles of fermionic dark matter can answer the Boltzmannian part can answer for the Milky Way rotation curve, while the central core can answer for the dynamics of the S star without the black hole? Well, we have to solve the boundary condition problems, but this is we have shown that this is absolutely possible. In this plot, you can see this typical profile I have shown. So there is a family of profiles with particle masses from 48 keV up to 345. So this dashed gray to black profile with corresponding rotation curves, where the outer, let's say, a diluted Boltzmannian halo can answer for the rotation curve with the addition, of course, of bulge and disk distribution. This is all the data matching. But also the central core can answer for the average circular velocity of the best resolved stars. This is S2. So this is very interesting. So you can have this degenerate core at the center of the halo, which is inside the pericenter of S2. But now let's well, this is a zoom of the rotation curve to see that the fit goes similarly well as the NFW. But recently we have went to look the geodesics of the S2 to see, to take all the data, and then we took the best 17 resolved S stars with all the data in ascension, right ascension, declination, and radial velocity, and compare the fittings of this central dark matter core respect to the average chi-square best fitting of a black hole. And it's very interesting that it's not only the central fermion core can answer for all these stars, but also the reduced chi-square is slightly better than the black hole. This is quite interesting, quite remarkable. I will give more details on this in a plenary session of Thursdays, but there are more details about stars, but I don't know how much time, Nick,
You have 3 minutes from your original talk and 3 minutes of question, which you can take. So 3 minutes until the end of your original talk.
Thank you, Nick. So I will 1 minute to say that it is possible also to apply these core halo profiles to different galaxy types, from dwarf to ellipticals. So what basically we have done is we have taken the 8 best result dark matter satellites, typical one halo scale length of 400 parsec and typical mass of 10 to 7. Analogously for spiral and ellipticals, of course, larger values of sizes and masses. And once fixing this value, we look for all the full families of profiles for a particle mass of 50 keV, the same that was fitted for the Milky Way, to see which was all the available cores that you can have inside of these halos and be in agreement with observation. And interestingly, for example, it's very interesting to see that in the case of dwarf, the mass of the cores go from 10 to 3, something 10 to 3 up to 10 to 6 solar masses. So it automatically leads to intermediate mass black hole alternative, then and then can end up to 10 to 8 solar masses, which is the critical mass of gravitational collapse because of the critical mass of gravitational collapse for a system of neutral fermions. You can easily show that this is for 50 keV, this is the mass, which is it may provide initial seed for formation of observed supermassive black holes in active galaxies. So we have I mean, we wonder ourselves if this may imply a paradigm shift in the formation and nature of galactic cores, meaning that galaxies, non-active galaxies, which doesn't show nor nuclear nor jets nor activity, may be simply cores of dark matter, quite dense but not yet collapsed. But instead, active galaxies, because are larger generally than 10 to 8 solar masses, the central objects, are indeed black holes, from our model would be from the collapse of the dark matter cores, and that's why this dichotomy. This is a suggestion that arises out of our model. And well, I think I will leave for questions the nature, which is maybe the nature of the Kievish fermions in terms of right-handed neutrinos that maybe there will be question about or not, and I will just.
You still have 1 more minute if you want to take.
Okay. Okay. Thank you, Nick. Yes. Sorry. Right-handed neutrinos. So one may wonder, is it possible to model these neutral fermions as right-handed neutrinos? So the answer is yes. In principle, our right-handed neutrinos are maintain the group invariance in the new MSM model of Asaka et al. And of course, U2 goes either for left and right, but you can have this the Dirac term or the mass term and the Higgs portal, and we have built a minimal extension by doing a minimal extension of this new MSM model, adding a vector meson, a vector boson interaction among the right-handed neutrinos. You can show that where the interactions is V mu J mu, it's a current, and it's a right-handed neutrinos. We work in the relativistic mean field approach, and you can show that for certain interactions among the neutrinos, the right-handed neutrinos, you can be still in agreement with the rotation curve of galaxy once you assume, right, that the right-handed neutrinos are interacting, without and only spoil the rotation curve for very large interactions, constants. And then interestingly, you can link the cross-section of this, the cross-section constrained by colliding galaxy cluster. You know that is an upper bound around 0.5, and by theoretical expectation of this cross-section from 4 fermion interactions, you can put constraint to the coupling constant of the interaction among the fermions, and And with these interactions, you can evade or relax.
Time is up now, so
Okay.
you may wrap up. Thanks.
Okay, so this is a relaxation of constraints from stellar neutrino with interactions, okay, thanks a lot. Sorry for a few minutes late, and wait for questions.
Thank you very much for this very nice talk and very comprehensive talk. We have time for one question, actually, or two.
I have one question.
Yes, please. Diego. Please.
Yes. Do you know if anyone has tried to do this, the generate fermions, I mean, with simulations, not only with the entropic argument, but with really trying to do things? I understand it's a very complicated problem, but yeah, at some point someone should do it. Like an embody, including quantum pressure.
Yeah, absolutely agree. My answer will be, of course, there is not known simulation of that, and I think it would be very difficult because the sizes of these degenerate cores are milliparsec, while sizes of typical solitons, as David shown, are typical of kiloparsecs, sometimes depending on the, and so they can, while the boson can be resolved, the fermions will be very difficult, but analogous treatment of Madelung representation for bosons, if the analogous for fermion may be treated, it's maybe some hope, but I don't know.
Okay, I'm afraid I have to cut it because of limited time. Otherwise, we have more questions tomorrow. Let's thank Carlos again for his very nice talk. And let me now pass to Dr. Joseph Johnson, who is going to talk to us about interacting dark sector, mapping fields and fluids, and observational signatures.
Okay, thank you. So I will share my screen.
Thank you.
Okay, it says I'm not allowed to share screen now.
Why? You've done it before. Did you?
Yeah. I think
it worked before.
Yeah. So
I don't know what to. Well, I can show. I mean,
it says you cannot share the screen while other participant is sharing.
Carlos, have you stopped sharing?
I'm very sorry. I'm very
sorry, you didn't stop sharing. Good.
Okay. Oh, that's why. Okay.
I thought that there must have been something. Good. Yeah. Thank you.
Okay.
Very good.
Hopefully now it's working.
Perfect. Absolutely. Thanks.
Okay. So first of all, I'd like to thank the organizers for this opportunity. So today I'll be talking about interacting dark sector in the late universe, mapping fields and fluids, and observational signatures. So this is based on a work done in collaboration with Professor Narayanan at IIT Bombay in India. So from the cosmological observations, we know that currently the energy budget of the universe is dominated by the dark sector components, that is the dark energy and dark matter. And we also know from the observations, currently, as we know that the interaction between the dark sector components and the ordinary matter is purely gravitational. But these observations actually do not rule out the interaction between dark matter and dark energy. And this interaction between dark energy and dark matter has been proposed as a potential solution for the Hubble tension. So in this work, we actually concentrate on developing a framework in which there is a equivalent field theory and fluid description of this dark energy dark matter interaction, and then we look for potential observational signatures of this interacting dark sector, mainly by looking at the evolution of the scalar perturbations. So by when we describe the dark energy dark matter interaction, the general method to do is that we assume that there is a non-zero divergence of the energy momentum tensor of the individual components of the dark sector. That means the energy momentum of the individual components of the dark sector are not conserved, but the total energy momentum of the universe is conserved, which is denoted by these two relations. So in literature, we see many dark energy dark matter interaction models, so which can be classified into two categories. One is derived from action formalism. In other cases, the interaction is introduced by hand using various cosmological parameters. So in this work, we look at the action formalism. So we start with a field theory description of the dark energy and dark matter. So which means that the scalar fields describe both dark energy and dark matter. And we then try to formulate a equivalent fluid description of the same, where the scalar field describe the dark energy, but the dark matter is described by a fluid. And we look at the background and perturbed evolution for such a model. So first we start from the field theory action. So in the field theory action, which is given in the bullet point 3, the dark energy is represented by the scalar field phi, and dark matter is represented by the scalar field chi. And the interaction between the two is denoted by the interaction function alpha. So such an interacting dark sector action can be motivated by starting at a higher derivative gravity theories like f of r chi model, as it is shown here in the bullet point 1. So here f is a general function of the scalar curvature r and the dark matter scalar field chi, and which can be brought into the Einstein frame, which we have here in the bullet point 3, by means of a conformal transformation. And the function form of f will determine the evolution of the scalar field phi and the interaction function alpha. So once we have the scalar field action, it is pretty straightforward to obtain the evolution equation for the scalar fields phi and chi, which represents dark energy and dark matter respectively, and which is given here in the bullet point 2. So as one can see, one can actually identify the terms which will appear in the standard non-interacting case where we have two scalar fields. And by looking at the so by comparing this evolution equation with the interaction to the standard evolution equations for the two non-interacting scalar field, one can identify the interaction interaction term itself, which is denoted by q nu, which is nothing but the divergence of the energy momentum tensor, which can of the dark matter scalar field, and which is given by the bullet point 3. So here the interaction function basically depend on the the interaction term depend on the interaction function alpha and its derivative and the dark matter scalar field. Now we need to check or we need to find out an equivalent the fluid description of the interaction between dark energy and dark matter. For this purpose, we define a dark matter fluid with the following properties, which is energy density ρm, and the pressure Pm, and the forward velocity u. So, so we define these quantities in terms of the scalar field chi and the interaction function alpha. So once we define this mapping to the fluid, then one can write down the energy momentum tensor of the dark matter fluid in the standard form. And one see that by taking the divergence of this dark matter energy momentum tensor, one can obtain the interaction term, which turns out to be the product of the trace of the energy momentum tensor of the dark matter fluid and the covariant derivative of the interaction function alpha. Yeah. So now in the beginning, I have said in the literature, we have the models which is obtained from the action formalism and the others in which the interaction is introduced by hand. So we have basically looked at some of the popular interacting dark sector models considered in the literature. So here we see that this mapping between fields and fluids are possible in many of the models, and in others the interaction is simply introduced by hand. In that case, we have to stick to the whichever description they are using. In this, when there is a mapping between the two, one can actually use field theory description or fluid description based on what we are doing and which one is convenient. Now we look at the cosmological evolution with this interacting dark sector. So for this purpose, we look at the spatially flat FRW metric. And for the study the perturbations, we consider the Newtonian gauge. So first we look at the background evolution. So again, the evolution in the field theory description can be obtained from the equations of motions of the scalar fields phi and chi. And we get equivalent fluid description, which is given in bullet point 2. So here again, the left-hand sides of these two equations is the standard equations for a quintessence model, which is filled with a dark matter fluid. And the difference comes from the interaction function Q bar, which is the background interaction term, which is given here. So, and for this interaction function, one can actually exactly solve the evolution equation for the dark matter energy density and obtain the evolution as given in bullet point 4. So here we can identify the standard evolution of a dark matter fluid in FRW universe, and which is combined with the interaction term. Its effect is determined by this exponential given here. So the a detailed so this background evolution in this model and its observational implications will be discussed in detail by my colleague Archana Sangwan in one of tomorrow's parallel session. So now when we look at the evolution of the cosmological perturbation, so again, as I said earlier, we'll be analyzing the evolution of the perturbations in the Newtonian gauge, and where phi, the capital phi and capital psi are the scalar metric perturbations. So again, we have on the left-hand side, we have the standard perturbation equation without any interaction, and on the right-hand side, instead of 0, we have the perturbed interaction function, which in the fluid description given by the bullet point 2. And one can easily go to the field theory description by just changing the variables. One just has to use the definition of the energy density and pressure of the dark matter fluid and substitute those expressions. Then one can obtain the evolution in the field theory description. So to see if we can potentially detect this dark sector interaction from the observations, we look at 3 perturbed quantities related to 3 cosmological phenomena. So the first one is delta M, which is nothing but the dark matter energy density contrast, which is defined by delta rho by rho bar, which is basically the matter energy density perturbations divided by the mean energy density of the dark matter, which will tell us about the structure formation in the universe. And the next one is weak gravitational lensing. We will look at weak gravitational lensing by analyzing the evolution of the lensing potential phi plus psi. Again, phi and psi are the metric perturbations. And lastly, we will look at the integrated Sachs-Wolf effect, which is determined by phi prime by psi prime, where prime is the derivative of these perturbations with respect to the conformal time. So for to have an idea of the effect of this dark sector interaction in the evolution of these quantities, we look at the evolution of the perturbations in the redshift range between 0 and 1500. And we study the evolution in interacting and non-interacting scenario, and we look at the difference of these two evolutions, so which is denoted by this delta quantities, which is basically the difference between these quantities in interacting and non-interacting scenario. And these are some of the results we have obtained. So
you have 3 minutes. Sorry, you have 3 minutes left. Thank you.
Okay, I'm almost done. Yeah. So first, so for this specific analysis, we have to assume a form of the dark energy scalar field potential and a form of interaction function alpha. So here we have assumed a inverse potential for the dark energy scalar field that is proportional to 1 by phi. And for interaction function, we have assumed a linear function. So a alpha of phi will be c times phi. And so we have looked at both a negative and positive interaction function and found that there are some instabilities when we consider a positive interaction function. So we have considered c equal to minus 0.6. So the first plot is basically the a-scale interaction function in the first order in perturbations. So as one can see, up to around n equal to minus 3. So n is basically the number of e-foldings, that is log a, or equivalently up to around z equal to redshift equal to 30 or 20, there isn't much difference. So the effect of the interaction term is negligible, but then it becomes significant, and then towards the current time, that is z equal to 0, it again comes down, and the interaction is stronger in the for the larger value of k, that is at the smaller length scales. And this trend is continued into the other 3 quantities as well. Again, for the density contrast, we see a significant difference in the evolution of density contrast between interacting and non-interacting scenario after around z equal to 20, and which is again repeated in terms of the quantities which determines weak lensing and the integrated Sachs-Wolf effect. So which shows that from as the availability of more and more accurate cosmological data is increase, so potentially one can actually observe the signatures of interacting dark sector from these observations. So now I'd like to conclude the talk. So basically through this work we have shown that the interacting dark sector can be obtained from a classical field theory action, which can be motivated by a higher order theory with a non-minimally coupled dark matter scalar field. And we implement the interaction between dark energy and dark matter by demanding that the energy momentum of the individual component of the dark sector is not conserved. And assuming that we show that there can be a one-to-one mapping between field theory description and fluid description of the interacting dark sector for a unique interaction term. And by looking at the evolution of the cosmological perturbations, we have shown that there is from the future observations, the signatures of the interaction between dark energy and dark matter can be detected. Thank you.
Thank you very much for this very nice talk and for keeping your time perfectly. Now we have 3 minutes for questions or comments. Are there any questions from the audience at this stage? Otherwise, I have a question. It is Lorentz invariance that made you assume that the dark energy field is a scalar one. Am I right? Or
sorry.
I mean, you assume that the dark energy field is a scalar. This is because you were motivated by Lorentz invariance, I suppose.
Yeah. So so the dark energy is, I mean, the so basically we have taken a quintessence model of dark energy. So in which the dark energy is represented by a scalar field.
Right.
And yeah.
But this is because you want the vacuum to be Lorentz invariant, I suppose. That's my question. I mean, it has to be a scalar field. That's the question.
Yeah,
It could not be. That's my worst question.
Yeah.
And in the quintessence type, you get it in by selecting, as far as I understand, particular potentials. Am I right? Or
Yeah.
Okay.
So we might, so for the to be consistent with the observations, for example, for the accelerated expansion,
right,
one will have to select a specific potential. So in this work, we have chosen the Rathra-Peebles potential, which is a inverse power law potential.
Very good. Any other questions? Well, if not, let's thank the speaker again and all the other speakers of this block, of this part of the block 1. So now we will break for 5 minutes, and we resume at 6:04 Central Time. Thank you very much.
Thank you.
Charged particles for later study in the lab. And then we have the TimePix array, digital camera array for monitoring the backgrounds from the beam. Nice thing about the experiment is we have a permanent physical record of new physics, and they maybe even trap new physics. And we have no standard model physics backgrounds, although we do have backgrounds that can disturb the measurement. We don't have anything that can mimic the measurement, really. So we ran for run 2, and these are the series of limits we came out with using the Drell-Yan production of monopoles. Here we have the magnetic mass on the vertical axis and the magnetic charge on the horizontal axis. And we can see that we probe up to charges of the order of 6 times the Dirac charge. The only competition we've got so far in the LHC is Atlas, that's put very good limits on charge 1 and charge 2. But we can see when we get, and you can see the limits here, but when we get to run 3, we expect to surpass these limits just with the Drell-Yan. But we can also, we've also placed the world's best published direct limits on multiply charged magnetic monopoles, as you see here, spin 1 monopoles, which no other experiment has actually produced a limit on. Drell-Yan plus photon fusion production of monopoles. Nobody's done photon fusion at production of monopoles at the LHC. Dion's electrically and magnetic charged particles, and I'm also going to talk about Schwinger production of monopoles. Another way we can produce monopoles, as I said, through photon fusion. And when we add photon fusion into the mix, we see that cross sections we manage to actually, even at run 2, more or less rule the roost, except maybe at spin 1. Yeah, even at spin 1. So, and again, Atlas has not at the moment produced a result on photo-produced magnetic monopoles. You can see the cross sections somewhat higher than the Drell-Yan produced monopoles. So the interesting thing at the moment is monopole production via the Schwinger mechanism. We know that we can produce electrically charged E plus E minus pairs in the presence of an extremely strong electric field. Well, when we have a collision of heavy ions, we have a very strong, extremely strong magnetic fields with fields as high as 10 to the power 16 Tesla, which beats any kind of nature-produced magnetic field, which is about 10 to the power 11 for a magnetar. So this is a very new process. What's exciting about it is that the cross-section calculation doesn't suffer from non-perturbative couplings as in the Drell-Yan model. I mean, it's essentially, I would say, a tunneling type of process as opposed to an interaction type process in the with the Drell-Yan. And what also it's this process is not suppressed when the monopole size is not point-like. So this we've now done the experiment. And of course, unfortunately, we didn't find a magnetic monopole. What that's allowed us to do is to place limits for the first time up to 3 Dirac charges on the production of monopoles that are finite sized and not necessarily point-like. And the paper, the preprint's out there, and the paper should be out within the next few months. The search for the Dion is something I've told you about. The Dion is, of course, is another Schwinger idea. It's a particle with electric and magnetic charge, and we've excluded Dions with magnetic charge up to 5 Dirac charges and 200 times the fundamental electric charge over this mass range. And we've also, in the same paper, excluded monopoles with magnetic charge up to 5 Dirac charges, and in this mass range. And CERN has nicely made a little notation for this in its website, which you can find on now. And this is the paper that was produced on that result. And we're now, another interesting item we're working on is monopoles trapped in the CMS beam pipe. There we want to take the search up to very highly charged monopoles, up to say 9 Dirac charges. We acquired the CMS beam pipe, and we've already analyzed the CMS beam pipe and found no monopoles, unfortunately. We did this by passing the broken piece of the beam pipe through a squid coil. Here we see the monopole going through a squid coil. And of course, as you would realize, as you know from your first year E&M at university, you're going to, when you put a magnetic field through a coil, a moving magnetic field through a coil, you'll get a current. This current, however, starts to flow and doesn't stop because it's a monopole. And of course, this is a superconducting coil. So that's the unique signature. Again, we didn't see it, but nevertheless, we can now put limits. We should now be able to place limits up to about 9 Dirac charges instead of about 5. So these are the materials that we're now working on. And we see a whole number of searches for long-lived multi-charge particles, long-lived heavy supersymmetric particles, and other kind of highly ionizing electrically charged particles that's now underway, and will carry on over the next years, leading into and including run 3. I think an exciting phase for us is the next phase of our experiment. We will reinstall the metal for phase 1, but we'll also install a milli-charged particle detector that Vasya talked about in the previous talk. And that's at phase 1. At phase 2, we'll deploy a long-lived particle detector in this UGC1 cavern. And for phase 3, we'll extend this long-lived particle detector all the way down the cavern. This enables us to get some very interesting results. This is rather good placing. The distance from this detector to the IP at LHCb is 55 meters, and it's roughly at an angle of 5 degrees to the beam line. So you've just seen phase 1 and phase 2. Phase 3, as I said, is where we extend the map detector down the tunnel. And this is the tunnels from another viewpoint, and you can see that we have quite a large extension down there. And instead of using resistive plate chambers, which have gas and of course are reasonably expensive, we're using very cheap embedded wavelength shifting fiber scintillator type structures that enable us to get resolutions on tracking of about 0.5 centimeter. But a lot more cost effective. So what can we do with our feebly interacting particle detector, the one that goes in phase 1? This is the detector that's going to look for milli-charged particles. You've already seen it. That is already showed you some of the limits that we can place. We can go down looking for this dark photons. These milli-charged particles that come from the dark sector that Vasya talked about. We can place limits going down to 10 to the -3 of an electric charge up to, in this range from about 1 to 100 GeV. We can also look for, in some models, heavy neutrinos can have large electric dipole moments. Electric dipole moments give rise to a small electromagnetic signature, which we can also detect. And here we see the exclusion for it with electric dipole moment on the vertical axis and the mass of the neutrino on the horizontal axis. When we get to phase two, where we have the long-lived particle detector, we can immediately start to process long-lived particle decays, as Vasir just discussed. And for example, we can look for Higgs or scalar production via B decays, where the Higgs decays to 2 muons, should we say, here in this decay. And when we look at the limits that we can place, we see from the MAP1 300 inverse femtobarns, we fill up the space between LHCb and codex, and we in fact more or less cover the codex area quite well and extend it up to overlap with LHCb. So is very competitive. And when we look at some of the other experiments below, this is essentially the coupling sine squared theta. We see Methuselah and we see Ship, and we see that MAP1, although not competing, not covering the same region as Ship, is starting to compete. And again, MAP1 with 300 inverse femtobarn is covering the space between LHCb and Methuselah, which has much longer decay lengths, detects much longer decay lengths. So if we go to MAP2 now, we see that when we extend MAP1 down the tunnel, we see that we're essentially covering the same region as Ship for this particular process, of course, and covering a large region of the Methuselah sensitive area, and also covering this region between LHCb and Methuselah. So we're sort of complementary to both the main LHC experiments and the proposed Methuselah experiment. When we look for pair production of right-handed neutrinos, again, the page, the reference is shown here, of an additional neutral Z boson, we see the limits that LHCb can impose, and then Methuselah and Phaser 2 and Codex B, and we see that MAP2 again is rather competitive and fills a role of moving between LHCb and Methuselah. So in conclusion, we've got a very nice detector that can now, for run 3 and run 4 and beyond, we'll have a detector, the metal map detector, that can look for highly ionizing particles with the metal detector, long-lived particles with the map long-lived particle detector, and mini-charged particles with the map mini-charged particle detector. So 3 clear new avatars of new physics. And the metal map physics program covers numerous exotic dark matter scenarios. I've showed you a few today in a complementary way to the 4 main LHC experiments. And also we've seen to some of the newer, larger, dedicated experiments that are coming up. Thank you very much.
Thank you very much, Jim, for this very nice and comprehensive talk. Now we have time for questions or comments. I have one. Although I know myself, just for the benefit of the audience, what's the time scale for MAP to be fully operational?
Okay, so the phase 1 of MAP, the time scale is now run 3. So we expect to have MAP up and running. That's the milli-charge section, and the metal reinstallation. They should be running in 2022 if LHC does start up in 2022. Phase 2 and phase 3, the moment the plan is that phase 2 will start later in run 3, and phase 3 will start for the high luminosity LHC. But it could be that with delays and so on, that phase 2 and phase 3 will get telescoped together and both start in run 4. So that's up for grabs at the moment. That's why I didn't say too much about it. But certainly, if you're looking in the not too distant future, we'll start up with a detector that can detect milli-charged highly ionizing particles, milli-charged particles, and maybe some small footprint in long-lived particles that will start up in run 3, beginning of run 3 in 2022.
Okay, thank you very much. Other questions or comments? Well, if not, let's thank Jim again for this very nice presentation. Now, let me apologize to Vaso because there was a glitch in the recording for her talk. But her talk, I asked her and she kindly agreed. She will re-record it, and so we will upload the recorded version as well of the talk in the appropriate platform. If we have time at the end, we may do it immediately after the end of the session. And I will also record the question by Carlos and myself as well for the benefit of the audience. So thanks very much to Jim again. And let me now go to the next talk by Daniel Gilman, who is going to talk to us about constraints of the dark matter self-interaction cross-section in low mass halos by using strong gravitational lenses, quadrupole images of strong gravitational lenses. Please, Daniel.
Thank you. Let me share my screen.
Please.
All right.
Very good.
All right. Great. Yes. Thanks for the introduction. So let me go ahead and get started. So just to be clear, I think that people use different acronyms in different communities, and in astrophysics and cosmology, when we say SIDM, we're referring to self-interacting dark matter. So it's not necessarily strongly interacting with a specific model. It's self-interacting, and the interaction cross-section is actually quite low. And the reason for that will become clear in a second, but you can think about the number of interactions per Hubble time. This is just going to be basically the cross-section weighted by velocity times some density times some time scale. And if you work this out, just putting in kind of characteristic values, if you have a cross-section per unit dark matter particle mass of 1 centimeter squared per gram, and you look at a density that's like the critical density of the universe, you get basically that these particles never find each other. And so what this means is that just in an average density part of the universe, self-interacting dark matter would behave like cold dark matter for cross sections of order 1 or even 100 centimeters squared per gram. But this is sort of done by construction because what people are interested in when they think about self-interacting dark matter is actually changing the density profiles of collapsed halos. So this is a dark matter simulation. You can see that there are these blobs of dark matter that are very dense to the background density. And these are called halos. And so a slightly more correct statement is that self-interacting dark matter behaves like cold dark matter outside of halos. And inside of halos, if you just start computing the number of interactions per Hubble time using kind of characteristic densities and velocity scales for these objects, you get order 1 interaction. And so you are able to now start changing the density profiles of dark matter halos in a variety of ways. And the way people study this is by running n-body simulations. So these are just, they track the nonlinear evolution of dark matter halos and their density profiles. And if you turn on self-interactions, the first kind of smoking gun thing that happens is you get a core. So the black dots here, that's just a regular collisionless cold dark matter structure. And you can see that as you start ramping up the self-interaction cross-section, you get a larger and larger constant density core. And this happens basically because the dark matter particles can exchange energy and momentum, and you have heat transfer that goes into the core and supports its formation. Over time, this can actually, the heat transfer can fail to support the core, and you actually get something called core collapse. So like relative to the cold dark matter structures here in black, right? First you form this core, and then over time they collapse and they become these extremely dense, extremely centrally concentrated structures. And the reason people are interested in this is, and the reason why people consider cross sections of order 1 centimeter squared per gram is one, you don't want to mess with the large scale structure of the universe because it seems to be, pretty consistent with cold dark matter. But on small scales, there are certain issues with cold dark matter. I'm not going to spend too much time motivating these problems. Basically, it can be advantageous for you to change the structure of low mass dark matter halos in order to reconcile some discrepancies that people observe in dwarf galaxies with respect to the predictions of CDM. And so one way to do this is just to change dark matter physics. And this plot here on the right shows one example of a problem that you can resolve with dark matter physics. It's called the core cusp problem. So if you produce a core in a halo, it seems to give you a better fit to the rotation curves of some galaxies than if you have a cuspy halo, which you would get in cold dark matter. So I want to switch a little bit now and start thinking about what implications self-interacting dark matter has for astrophysics. And this idea, I like to go back to this paper by Manoj Kapling-Hatt. And the idea is that if you have different halo masses, they have different velocity dispersions. And so they act like particle colliders with different beam energies. That's borrowing the language from this paper. And so what this means is you can actually constrain the velocity dependence of the cross-section by making astrophysical observations on different scales. And it's illustrated with this figure. So on the x-axis is the kind of the characteristic velocity, which you can also think of as a mass, because more massive halos have particles moving more quickly inside of them. And you can see that in galaxy clusters, these are kind of inferences or constraints on a possible self-interaction cross-section. And if you follow these black lines, those correspond to a velocity-independent cross-section. Okay, so if you look at the green points on the far right, those come from galaxy clusters. They require like 0.1 centimeter squared per gram, but not larger. And if you want to reconcile small-scale structure challenges to cold dark matter, you need something like 1 or 10 centimeters squared per gram. And so you see that with a velocity-independent cross-section, you can't do this. But if you put in a velocity-dependent cross-section, which is, so one example is this yellow line that cuts through the figure, you can actually, get really low amplitude cross-sections on cluster scales, and then a large cross-section on subgalactic scales, and you can potentially explain some small-scale anomalies with respect to CDM. And there's one thing that you can notice on this figure is that there's basically no data points down below relative velocities of 50. I mean, okay, so there's one here, but once you get much lower, you don't see any data points. And the reason is because halos that are that low mass don't have stars in them. And you can't infer the density profile of a dwarf galaxy if you can't measure its stellar dynamics. So at a certain point, you run into this basically a brick wall that prevents you from learning anything about the density profile of low mass halos because they're invisible and you just can't see them because they're so dark matter dominated. And so if you want to kind of extend this figure to lower velocities or lower halo masses, strong gravitational lensing is going to come and it's going to rescue us. So I assume that people, maybe they've heard about strong gravitational lensing before, maybe not. I like to start with this short video as a quick intro. So as I play this video, you'll see a fish approach the corner of the fish tank. And as it approaches the corner of the fish tank, you'll see two images of the fish appear. Okay, so there's only one fish, right? But the light is leaving the fish and it's taking multiple paths through the water and then through the fish tank. And then eventually we see two fish instead of one fish. And this is basically what's happening in strong lensing, right? So in just regular lensing, you have a deflection of light by the gravitational field, and this will cause a displacement between where you observe a luminous source and where it actually is if it's behind some massive object. Okay, so in strong lensing, you have a more precise alignment between the source and the massive object, and you actually get multiple images of the source. And these multiple images will be highly magnified, and it's a very extreme effect. So I mean, you can see it by eye here on the right. This is a pretty famous lens, RxJ1131. And then just to be clear about what's going on here, the thing in the middle is just a regular galaxy. It's producing these multiple images. Then there's 4 images of a single background quasar. So this is a quadruply imaged quasar. And in this case, there's actually a galaxy around the quasar, which itself is lensed. And so you get this arc or an Einstein ring, right? And these galaxy scale strong lenses are very powerful tools for studying dark matter science because they're probes of substructure. So if you were to zoom into a dark matter halo, you might see something like this on the right. And this kind of structure would exist in cold dark matter and self-interacting dark matter. Except, you know, the density profiles of the self-interacting dark matter halos would be altered relative to cold dark matter. And you can imagine that if this population of halos is out there around some galaxy and there's a lens, and that galaxy is acting like a lens, the gravitational impact of these halos is going to affect the way the image appears to you. So it'll affect both the brightness of the arc or the brightness of the Einstein ring. And the effect that I'm going to focus on for the rest of the talk is how it affects the image brightness or the brightness of the 4 images of the quasar. And I have a quick movie that illustrates this. So what I'm going to do is drag a very low mass halo across a simulated lensed image. And at each position, I'm going to ray trace and compute the magnification of this image. And you'll see on the right what happens as the halo crosses the image. And then on the left, this is the magnification cross section for this halo. If I play the movie, see the halo comes in, it gets close to the image. Something interesting happens right as it gets on top of the image, and then it leaves, and then the magnification goes back to whatever it was without the halo present. And the point is that this halo is 10,000 times or so less massive than the galaxy that's producing the multiple images. And so by studying the image magnifications, we get a very localized but extremely sensitive probe of very, very low mass structure across cosmological distances. And this kind of halo mass would have a velocity dispersion of order 1 kilometers per second. And so if we can somehow detect self-interacting dark matter structure in these very low mass halos, we can study the self-interaction cross-section at very low relative velocities. So that's kind of the idea behind this work. And I'll just say here that the movie I showed you was for a single halo in the plane of the lens crossing an image. But the kinds of simulations and the results I'll show you are based off of 3D simulations where we have structure along the entire line of sight, and we ray trace through all of it to compute the lensing observables and to do our simulation. So here's just a 3D representation of a lens. And then the one other thing I'll say about this is because it's you're probing distances of several gigaparsecs, and so these are time scales of several gigayears. And so you can actually, in principle, study the temporal evolution of self-interacting dark matter halos over the age of the universe because the light has been traveling to you for so long. Okay, so what I'm going to talk about now is a paper that we wrote about 2 months ago. And we're basically just exploring the implications of self-interacting dark matter for strong lensing. And to do this, we assume a specific form for the cross-section, which you can think of this as just a weak long-range interaction with kind of a generic form where it's velocity independent at low speeds and then drops like v to the 4th at high speeds. And all the structure formation stuff that I'll discuss depends only on this thermal average of the cross-section. So it's essentially the velocity-weighted cross-section where you assume a Maxwell-Boltzmann distribution, and then you integrate over it. And the halo mass comes in because of so basically more massive halos have higher velocity dispersions. And so that tells you what kind of the characteristic velocity of the particles is in that halo. And what you can do with this kind of cross-section is have something that reaches very, very high amplitude at low relative velocities and low mass halos, and then falls off very quickly at high relative velocities. So you can evade constraints on the cross-section from clusters and galaxies, and then get extremely high cross-sections on the mass scales where basically only substructure lensing is able to detect dark matter structure. And so in order to do lensing stuff, we have to map this cross section into halo density profiles. And so, as I said before, there's cores and then core collapsed objects. And so I'll go through both of these possibilities now. To compute the cores, we use a fitting function. I wouldn't call it a theory of structure formation. It's really more of a fitting function for the core densities. And you basically say, okay, I'm going to find some radius where dark matter particles are scattering once per Hubble time. And then I'm going to use the Poisson equation plus the radial Jeans equation together with that characteristic radius R1 and some boundary conditions on the density profile at R1, and I'm going to get out a core density. I don't have time to go through the details, but this is basically how it works. You can read it in Manoj's paper or the one that we wrote to get all the details. And if you do this, applying, here are the three cross sections that I looked at before. They have different amplitudes and different velocity dependences. You can get the core size as a function of halo mass. And you can see that, so that raising the amplitude of the cross section just rescales all the core sizes, but then the velocity dependence tells you the slope of the core size halo mass relation. So the next part is core collapse. And so to do this, we use a characteristic timescale, which is just the relaxation time for the halo. And we use the results by a paper by Nishikawa et al., and where they basically tracked the temporal evolution of halos and figured out when they core collapsed. And so tidally disrupted halos tend to collapse after order 10 relaxation times, and field halos, which are just pristine objects that are undisturbed in the field and not orbiting a galaxy, they tend to collapse about a factor of 10 later. And so we just assigned a core collapse timescale of 10 relaxation times to subhalos, and then to objects in the field or along the line of sight, we said that they collapse after 100 relaxation times. And so you can see here that the relaxation time itself depends on the normalization and velocity dependence of the cross section. So here the color scheme is the same, right? So if you have a very long relaxation time, it means that basically that it never core collapses. And so, if, for example, this black model, very low mass halos core collapse very quickly, but then once you get above like 10 to the 8, then they would never core collapse, or they would be unlikely to core collapse within the age of the universe. And here is, if you take that relaxation model, and then you just compute the fraction of core collapse subhalos as a function of the main deflector redshift, you can produce these curves. And you can see that, for kind of reasonable numbers, you get something like 20% to 10% of subhalos core collapsing. And then, finally, once we've identified an object as either being cored or core collapsed, we assign it a density profile. So the regular cold dark matter profile here is in gray. The exact solution to the radial Jeans equation plus Poisson equation is black, and we approximate it with this dashed black line. And then if an object has core collapsed, we turn it into this, dotted black profile. So you can see that it becomes extremely dense. It actually has a logarithmic slope of around -3, whereas the NFW profile has a central slope of around r to the -1.
You have 3 minutes.
All right, thank you. And what you can see here is that core collapsed halos are extremely efficient lenses. So what I'm showing you here is the magnification cross section. So if you have an NFW halo in black, and then if you had a core, right, it's less dense in the center, so it becomes a less efficient lens. But if you now make it core collapsed, it becomes extremely centrally concentrated, and its lensing signal is around 5 times higher than a regular NFW halo. And another way to visualize this is to look at projected mass. So here is just a projected mass distribution in cold dark matter. In the center here, I'll turn on core formation, but not core collapse. So now every halo has a core. and you can see that everything looks smooth in the lens. And then this black line is the critical curve where the images appear. But now if you allow halos to core collapse, you get stuff like this. So you can see that they produce strong distortions in the critical curve. And sometimes these core collapsed objects actually have their own critical curves, which means that they themselves can produce multiple images and act like strong lenses. So I'm running a little low on time, so I kind of have to breeze through the next couple of slides to get to the results. But basically, what we do is we combine this specific model for SIDM physics with our structure formation model, and then we do a bunch of lensing simulations with it using simulated data sets to figure out, to what degree we can use lensing to constrain the cross section. And to do this, we have this big forward modeling inference pipeline, which I don't have time to describe, but we basically just generate hundreds of thousands of realizations of SIDM structure and then compute lensing observables from it and then do statistics to match the flux ratios. And an example inference that we get is here. So this is on sigma 0 and V0. This is the amplitude and velocity dependence of the self-interaction cross-section. And here I put in truth, which was cold dark matter. So basically very low cross-section on all velocities. And you can see that you rule out, high amplitude cross sections with a large V0. So you basically rule out very efficient self-interactions. And to quantify this better, I cast the constraints in terms of sigma 20, which is the amplitude of the cross section at 20 kilometers per second. And you can see here that once you get up to around 50 lenses with mid-IR flux ratios, we can start to rule out something like 10 to 20 centimeters squared per gram. And then, so that's a sample size that we'll have in a few years. And then we can do the same kind of forecast for ruling out cold dark matter. So if we detect, a positive detection of a cross section, we can phrase this result as a relative likelihood. So, how much more likely do we believe self-interacting dark matter is relative to cold dark matter? And you can see here that you reach relative likelihoods of around 20 to 1 or 10 to 1 if you have mid-IR flux ratios. And I didn't say this earlier, but basically the mid-IR flux ratios are more sensitive probes of substructure because the source is more compact. And so you're more sensitive to small perturbations in the image. So, okay, I think I'm just about out of time. So I'll just leave the take-home messages up here. This was more of an exploration work. We were proposing strong lensing as a probe of self-interacting dark matter, and I think we showed that it is a promising tool to go and study the self-interaction cross-section at low velocities. So thank you.
Thank you very much for this very, very interesting talk and very interesting approach, which I enjoyed. Carlos.
Yes. Hello. Thanks a lot. Yes, Daniel, for this nice presentation. I want to ask about, probably if you know about this, one of the recent paper about the group of Piero Rosati over a small scale excess of gravitational lensing towards the center of galaxy clusters, where there is a magnification near an order of magnitude respect to the what we expect from lambda CDM simulations. Your self-interaction, if your self-interactions can account for that, or have you tested this? What is your opinion about? Thank you.
So, right, so I guess there's two comments about that paper. So first of all, in galaxy clusters, the strong lensing cross-section is dominated by baryons, right? So dark matter halos themselves don't really get dense enough unless they core collapse to give you a strong lens. And so when you look at the strong lensing cross-section of a cluster, you're looking at the baryonic mass, basically. And so it gets very complicated to make inferences about dark matter physics when you have so much baryonic physics happening on top of it.
Sorry, but
yes.
Can I comment on that short? Because but
let me just finish answering the question.
Yeah.
So then the other thing I would say is that immediately after that paper, two other papers came out and said that this was an artifact of the simulations, and that if you use a higher resolution simulation, you actually don't get this order of magnitude difference. And so for me, that result was reminiscent of other kind of anomalies with respect to cold dark matter that happen because simulations are really complicated to run, right? And to connect to observations.
Oh, okay. Well, I should read these later papers, as you said. But my short comment is that in that paper, they also ran over the lambda CM aerodynamical and simulation considering baryons in different prescriptions. So, you know, the up to them, the excess was still there, either including baryons. So, but anyway, probably, yeah, have to check these second papers. Okay, thank you.
Okay, thank you very much. Sorry that we don't have time for further questions. Now, unless there is some urgent one or an urgent answer of Daniel to the comment by Carlos.
No.
Okay,
I think it's
good.
a fair comment.
So let's thank Daniel again for this very nice talk and nice approach. And let me now invite the last speaker of this session, Dr. Shreya Banerjee, who is going to talk to us about the growth of linear perturbations in a universe with superfluid dark matter. Shreya.
Yeah. Can you see?
Yes, indeed.
Yeah, great. So thank you very much. And also I'd like to thank the organizers for allowing me to present my work in this over here. So this work has been done in collaboration with Dr. Shantini Bera of ICRANet Pune in India and Professor David Mota of Oslo from Norway. So as the title reads, I will mainly be talking about how the linear perturbations, how the growth of linear perturbations occur in the model of superfluid dark matter. So briefly going to the motivation, so why we mainly want to study this particular perturbation theory using this particular model. So as we know that in standard CDM, we know that it explains the cosmic history quite well at cosmological scales. But we also know at the same time that there are certain problems at the galactic scales, like for example, the baryonic Tully-Fisher relation or the Cusp core problem or the too big to fail problem. So I won't go into the details. So I think most of you all know about these problems. On the other hand, at the galactic scale, we know a particular theory known as the MOND or the modified Newtonian dynamics, which we all know that it modifies the Newtonian force law between two massive bodies at non-relativistic limit. So it can explain the galactic dynamics pretty well. However, it fails to explain CMB observations, and the relativistic extension of such a theory is also missing. So the main aim of this particular model was to address these issues of both CDM and MOND while being successful at both the cosmological as well as small scales. So basically it was the theory is a CDM-MOND hybrid. And this class of models also take into consideration the interaction of the dark matter and baryon together, where the interaction is through a MOND-like force, which is mediated by inclusion of a new interaction term, which I will be showing shortly. So I'll briefly go through this model, which was mainly proposed by Justin Khoury and Bereziani some time back. So this dark matter behavior of dark matter as superfluids, it mainly consists of microscopically, it's made up of very light axion-like particles. And as we know that like superfluids, they also undergo a phase transition at particular temperature and hence a particular specific scales. So the behavior depends on whether we are at the galactic scale or different scales. So at galactic scales, it was shown that the superfluid behavior, at the galactic scales, the behavior remains, and the DM can be described as collective excitations or phonons rather than individual particles. So basically they behave like a condensate, and these phonon modes mediate a Mondian-like force between the visible matter by coupling to the baryons. So basically all the interactions between different baryons occurs via the phonon mediated force. However, in clusters, because it's a larger scale, hence the dispersion due to high dispersion velocity, hence high temperature, the DM then here consists of mostly normal fluid compared to superfluid. Therefore, there the DM is best described as particles. It has widely been studied at the galactic scale. So in their work, they have described many observational signatures that this model itself has at the galactic level itself. But since I will mainly be studying its application at the cosmological perturbation theory, so I won't go into the detail of the galactic constraints that one can get on this model. So I will straight away go to the Lagrangian with which we have worked in this theory. In the non-relativist regime, so this is basically described by phonons and by the scalar field theta over here. So this Lagrangian is basically given by this equation 1 over here, and by this x is, as you can see, is defined with respect to the temporal and spatial derivative of the scalar field, and this phi being the gravitational potential. So this px now has the form is given by equation 2 over here. So it is the fractional power of x. So I will shortly explain why, the reason behind this fractional power, and find where this lambda here represents basically the range of interaction for this phonon. And as I said, that there is an interaction, the phonon also gets coupled to the baryons, and so coupling occurs through the interaction term given by equation 3, where alpha corresponds to the coupling strength over here. So the main motivation behind the choice of this Lagrangian is that the power of this Lagrangian is defined in a way that the equation of state represents a 3-body interaction. So it's like P is proportional to rho cube here. So such that the 3-body interaction is basically through the baryons mediated by the phonon. And we have seen such fractional powers of 5/2 earlier also, for example, in ultra cold atoms, where they also behave like superfluids. So, however, in this case, the choice is arbitrary, but the main motivation behind this choice was that the superfluid dark matter should give rise to a Mond-like dynamics at galactic scales when baryons are also included. And the interaction terms also similarly ensures that the Mondian force between the baryons and between the baryons are also mediated by the phonon that finally gives rise to a Mond-like force. Finally, as we can see that there are basically 3 free parameters of this model: the mass, lambda, that determines the range, and finally the coupling strength. However, we know, because we are dealing with axion-like particles, so we have some idea about this M. However, the other 2 have been constrained at galactic scales, but at the cosmological scale is something that we want to constrain. So from the background cosmology itself, we can put some bounds on these model parameters. So as we know that at the background level, the cosmology is well described, the DM is well described as a dust, it behaves like a dust. So this equation 4 represents the equation of state for this condensate. And for it to behave like a dust, if we consider that we choose the initial condition at the matter radiation equality, where rho equality, you know, it's given by 0.4 eV4 from the observation. So we easily get a bound directly from the equation of state given by equation 5, as you can see over here. So as you can see, this gives a lower bound on this parameter that determines the range, and it is dependent on the mass of the phonons. So for example, if M is equal to 0.6 eV, then lambda should be much greater than 0.5 eV. So this gives a lower bound, and similarly we can also get a bound on this alpha interaction parameter. For this we go to the background equation of motion for the theta, which has a solution given by equation 7 over here. As you can see, this represents a dust part, and this is the part that comes from this model, the interaction part. So from here in equation 8, you can easily get the total density behavior. So, but we know once again that the background should be mainly dust, behavior should mainly be dust-like. So for it to behave, this term to be dominating, one should have negligible impact of this term over here. So from keeping the earlier bound of lambda in mind, so we can directly get a bound on alpha also from this background equation itself, which is given by equation 10 over here. So this gives a upper bound on alpha parameter. So as you can see, for this, once again we assume the bound on lambda, which we already got earlier, and we consider the present value of rho b by rho dust at present. So considering this these bounds, so now we want to check what happens when we go to linear perturbation theory. So for this work we have remained in the linear regime. Of course, one can go to the total nonlinear regime and then check recheck whatever. This will be like a limiting case for that. But at the first approach, we have worked with the linear order only, because we mainly wanted to see numerically as well as analytically what impact it has already on the bounds that we get over here, whether they still give rise to observations that is similar to lambda CDM, or there are some significant distinct features of this model that we can see at this level itself. So for this, because this is fluid dynamics, so we go directly to the Hamiltonian picture over here. So as you can see, equation 12 gives rise to the Hamiltonian, where pi theta here corresponds to the conjugate momentum for the theta phonon field over here. So from 13 we get the Hamiltonian equations of motions. Now since we want to get the continuity equation and the Navier-Stokes equation over from in this picture, so we go straight away to define the hydrodynamical variables for this case. So equation 14 gives the two definitions corresponding to the mass density and the velocity, the forward velocity of the fluid. Similarly, one can also split the background, the gravitational potential and the forward velocity into the homogeneous part, the background part, and the part that comes from the inhomogeneities, which is here represented by phi. And of course, for the background, we choose FLRW background for this case. And here, the first term represents the normal Hubble flow, and this V represents a peculiar velocity. So keeping these changes in mind, then we get the first equation 16, the continuity equation, and the 17, we get the Navier-Stokes equation. At this level itself, we see that there are some distinct modification, additional terms that comes from this model, which contains the model parameters over here. But to study it further, to compare it with observations, we of course need to further perturb the field variables also, the field as well as the density. But we consider that this delta theta, delta rho m, and delta rho b, they are all small perturbations at linear, because we stay at linear order, as I already said. So the evolution equation, final evolution equation with respect to the relative density, the growth rate over here corresponding to this matter part, is basically given by equation 18 over here. So as you can see, there are distinct additional terms over here and one can get the expression for the sound speed, which is given by equation 19. And as you can see, it also depends on the model parameter lambda. So for certain possible values of m, for m equal to 1 eV, from the bound, we satisfying the earlier bound for the background lambda, which we already have, we set lambda equal to 500 to see the behavior of the sound speed, what values we see in the range of redshift that we are interested, that starts from the epoch of equality to the present time, present redshift. So as we the value of sound speed is very small, and thus we can set this term as we can neglect this term as far as if we want to get some analytical result at first. So this is what we do in the next section, where we study the analytical solutions at first. So there are basically two cases, without the presence of baryons and with the presence of baryons. So of course we set the sound speed to be much less than 1, so we neglect that term. So I will directly go to the result that we get from this analytical solutions, which has been coded in this equation 21 and then also in equation 22. So this basically, no baryons basically corresponds to the no interaction also, because the interaction is mainly through this phonon and baryonic interaction term. So as we see, in the absence of any interaction, this SDM, or the superfluid dark matter, behaves exactly like lambda CDM in the absence of baryons. However, if we include interactions and we keep the presence of strong interaction, and then we see that the growth is much more steeper. It grows as a to the power 5/2. So we see that the presence of strong interaction predicts the formation of structure at a much earlier epoch. So as we can see that from analytical solutions, we have the interaction term has a definite impact on this, on the relative growth of the perturbations. So we want to study it more detailed without any approximations that we have obtained over here. So we then, so before going to that, here is a plot of the corresponding, the result of the analytical solution that we get with respect to redshift. So this red line corresponds to the value for lambda CDM, and this dotted line is what we get from this SDM. So, and these are the values of the parameters satisfying the bounds that we already have. So as we can see that the perturbations in SDM grow at a much faster rate as compared to lambda CDM. So next we go to the numerical solutions to get more exact results. So for that, we of course go to the redshift coordinates and then to the physical coordinates, and these are the two equations that we have at our hands. So in order to solve the numerical solutions, we set all the initial conditions at the epoch of equality, which is at z equal to 1000. And because we saw that the main impact was for the interaction term, so we said choose the other two parameters. We choose the, or before solving the numerical solutions, we set the other two parameters, m equal to 1 eV and lambda equal to 500 eV. They both satisfy the bounds that we have already obtained. And then we see that how the variation of the interaction term basically varies the growth rate. Also, we said that delta B and delta M at the epoch of equality for the initial condition, which from observation we know it's 10 to the minus 5. And also at the background level, we already know that it's mainly dominated by rho M. So we set the background density as approximately given by rho M. And we choose that the behavior of the delta B and this rho M at the background level is just similar to what we have in what we get from normal CDM behavior. So though for the evolution with respect to redshift, we needed to choose a particular K, which we fixed it at 0.0001. However, at a higher value of K, the results are nearly almost same. So I will straight away go to the plots that we get, where here we have shown the ratio of the growth rate in superfluid to that in lambda CDM with the variation of the alpha parameter value. So we also need to keep in mind that they obey the bound that we already, upper bound that we already have from cosmology. So for a m equal to 1 eV, from the bound we see that alpha can be less than equal to 10 to the minus 4. However, we see that at 10 to the minus 4 value, the deviation from lambda CDM, which is represented by this black dotted line over here, it's huge. So if we keep on lowering, we see that it matches the lambda CDM exactly at around alpha equal to 10 to the minus 8. So we see that what was a possible bound for alpha earlier from background cosmology is actually not a favorable bound when we go to the linear perturbation. So the results are quite a lot of deviation.
You have, you have 2 minutes. 2 minutes left.
Yeah. So I'll straight away go to the matter power spectrum from here. So the results are just similar what we already got. So for this case also, as we see with increasing in value of alpha, the deviation from this lambda CDM value, which is represented by the straight line over here, increases, and the match is nearly exact when we go to the into the minus 8, alpha equal to into the minus 8. So quickly, the results that I have, I'll quickly read, summarize once more that for the plot for alpha equal to the minus 8 coincides with lambda CDM. So the deviation is very small, around 0.13%. When alpha is large enough, the growth is very steep, ensuring that structure formation takes place at an earlier epoch. However, this value is different from the value that was quoted in the Corys paper. The bound, as I already said, that the bound that was obtained there for m equal to 1 eV is that alpha should be less than equal to 10 to the minus 4. However, here we see that such a value of alpha strongly deviates from lambda CDM in the context of perturbations. Similarly, the power spectrum reaffirms the earlier obtained previous results that the alpha equal to minus 8 provides the most accurate fit, and the in general the power spectrum approximately increases linearly with k. However, for large enough alpha, it becomes relatively flatter. So as we know, these were just results from perturbations. However, we want to obtain more stringent bounds and more, not only from cosmology, also from other observations. So one of the way that one can approach is constrain, now go to further step and constrain it directly from CMB observations. And of course, go to nonlinear regime. And a thorough study of gravitational lensing is also a way to constrain, put further constraint on this model. And something that we are currently looking at is how the behavior of the, how one can constrain the model parameters from the current LIGO observations that put bounds on the gravitational waves at the speed through the behavior of the gravitational waves through a superfluid medium. So this is something that we are currently looking at. So that was all. I will finish my talk with these future directions. And so thank you for your attention.
Thank you very much for this very nice, interesting, and very clear talk and nice physics. Now the talk is open for question. I think David Mars, Dodi has a question. Dodi.
Hi, yeah, thanks for the talk.
Yeah.
I don't remember the details, so I'm sorry, but there was a paper by Mark Hertzberg claiming something to do with superfluid dark matter doesn't actually match rotation curves. I don't know if you know the paper, if you have a comment on it.
I think it was for a particular case, but not for this particular Lagrangian, which we have been working with. So the chosen Lagrangian was different. So that for that particular case, it was showing some contradiction with the observations that we already have. Yeah.
Right, but it depends on the particular form of this kinetic.
Yeah. So like, yeah, there are some other forms also, but this particular form is something that has satisfied till now all the observations at galactic scales, at least.
Okay, thanks.
Other questions? I have one, actually, a very short question before we finish.
Yeah.
Are you aware of the Bose-Einstein condensate works for actions by Sikivi collaborators?
Yeah, I have seen papers. Yeah.
Because they were claiming that cephalor actions of actions could lead to Bose-Einstein condensate when the temperature is about 500 eV. So I was wondering whether your Lagrangian can under some circumstances lead to Bose-Einstein condensates as well. I don't know if this is possible. I mean,
one thing is that the bosons for BC, it's like the equation of state is like more P is proportional to rho square. But for this case, because the main thing is this, as you saw, the baryonic interaction, the three force, so that's very important. So that's the main difference. So it will be difficult to like if we go to that regime, the three body interaction, that main aim would get like.
But you might have, in a sense.
Yeah, you might, because
it's not feasible to study.
Yeah.
I see.
Yeah.
Thank you very much. Any other questions? Well, if not, let's thank all the speakers of this session for their very interesting talks. And I will see you all tomorrow. Now, before we close, because there was this glitch on the talk by Dr. Michu, she kindly agreed to re-record her talk just for your sake, and we can do it now. I got special permission for some extra minutes until Dr. Michu re-records her talk. I have to apologize to her and thank her for her willingness to re-record the talks. You don't have to stay, of course. The session is finished, unless you want to, of course. Those of you who want to stay, I will also recreate the question by Carlos and myself for this talk. So if Vaso is now the session is over. If you want to stay, of course, is your you have heard the talk. Let me invite you again to talk about LHC experiments for the dark sector, and this time is recorded.
Okay, thank you, Chair, for this second opportunity. This time on the record. Okay, so I would like to thank the organizers for this, the organization of this nice. Event, and also for the kind invitation. So I'm going to discuss the dark sector in some very specific experiments, LHC experiments that target long-lived particles. So to set the stage, as we know, the experimental world can be divided roughly into three frontiers: the high energy frontier, LHC, etc., the intensity frontier, the factors, etc., and the cosmic frontiers, astroparticle experiments. And let me add here a different concept, a fourth frontier, the lifetime frontier, which of course it is entangled with the other ones. So to be more precise, let's go to the LHC world. So here we have the general purpose experiments, Atlas and CMS, and also CP evaluation experiment, LHCb, that are mainly optimized for new particles that decay promptly. That is, they are strongly coupled. Despite that, thanks to the development of new techniques and strategies for trigger reconstruction and analysis, they have also managed to partly cover the long-lived particle world in the heavier part of the parameter space, but still there is much to be explored in the forward region and in the transverse. And this is where new dedicated experiments come into play. To be more precise, we can discuss two kinds of experiments where they try to detect the decay products, the visible decay products of a neutral state that has passed through various detectors, rock, you name it, and then they are giving rise to a displaced vertex, but also experiments where they try to directly detect signals of anomalously ionizing particles, highly ionizing particles, or milli-charged particles, as I will discuss here. So in the dark matter world, how does this fit? So as you know, there are complete dark matter models, supersymmetry, for instance, extra dimensions on one side, that they have very specific and very well defined dark matter candidates. But when trying to interpret the results of searches in collider experiments, we have dark matter effective field theory, something much more abstract. Somewhere in between, we have simplified dark matter models, and within this category, there are some portal, as we call them, models, where a new particle is long-lived due to the weakened coupling with the standard model particles. So these are feebly interacting particles, FIPS. So dark photon, dark scalars, Higgs portal is in this category. To be more precise, here I will give you some more details on that. So dark photons, they are U1 gauge group that they are added to the standard model Lagrangian, either directly through a kinetic mixing term, or this term occurs at the loop level. So they allow the coupling between this A prime with the gamma and Z.
Excuse me, the connection will close automatically in 10 minutes. So maybe you can speed up a little bit.
Yes, sure. Okay, light neutral Meson decays. This is the way that these particles are produced, and this category will also have milli-charged particles. The dark Higgs is something similar, where singlet scalars are added to the Lagrangian, and again they are produced in penguin decays of mesons, and they end up in the decay of fermions. There are, of course, other portals like heavy neutron leptons or axion-like particles, but in this talk I will concentrate on dark matter particles. So the experiments themselves, you can see them in the summary here. There are pretty many of them, and one would think, why do we need so many of them? It's because they have different angles with respect to the beam axis, forward, transverse direction, different volumes depending on the available space that exists, the distance from the IP, and therefore they probe different range of lifetime couplings to standard model and boost, which is directly related to the mass. Some of these experiments also measure neutrinos, like the SMD at C and the phasor nu. And it's worth to mention, before going in detail, Other non-LHC experiments, SHIP is one of the big ones. Let's say other they're already running, another they are planned to be installed in future colliders like FCC. So let's go into detail. So MAP, MEDAL apparatus for penetrating particles. So MEDAL was the first dedicated experiment at the LHC for searches of new particles. It consists, the MAP, an extension of MEDAL, consists of two main detectors, the MAP long-lived particles, LLP, and another core milli-charged particles detector. I will not say much of this because Jim Pinkford will or has already given a talk on this in detail. Phaser, it's a forward search experiment at the LHC. It's approved. So it's in a very forward region, around 500 meters from IP1 Atlas. It is very thin, and it is going to be upgraded for high luminosity LHC Phaser 2 to have a much bigger volume over a radius of 1 meter. And it has already published some results from the Phaser New, the neutrino extension of this experiment. SMD at LHC is a similar experiment in the other side of IP1, another 500 meters, but not that forward. It is a small-scale prototype of the SIP experiment SMD. It's been planned to do mostly neutrino physics. Here you can see how it compares its reach with Phaser. You can see it's not that competitive, but remember that this is mostly a neutrino experiment, let's say, than LFP experiment. FACET is the latest proposed experiment. This is much closer to the IP and much larger decay volume than Phaser, and we will see if it be approved. It will operate at the high luminosity LHC. Codex B, this is an RPC resistive phase chamber experiment, a box of 10 by 10 by 10 meters in the transverse direction this time, in the LHCb interaction point. A sealed lead seed is expected to absorb some of the background.
5 minutes.
And there is a
5
Codex
minutes,
B.
and it will close automatically. 5
Okay.
minutes. So please wrap up.
Codex Beta demonstrator is planned for round 3. Methuselah, the larger of this experiment, is in the surface, so it has pretty much space to cover, and around 100 meters away from the CMS interaction point. Demonstrator has already run near Atlas, and it has proved that the concept of this experiment. The newly addition here is that if an RPC layer is added, then one can do cosmic ray physics by detecting extensive air showers with this detector, not just LLPs that come from CMS. Anubis is a proposal to cover this shaft of the Atlas cavern with RPCs that use the same technology as Atlas, and also use the Atlas clock as an active FITO. And also it is planned to install a demonstrator for round 3. ALEX 3 is a rather conditional experiment. If ALICE finishes its physics program before the end of high luminosity LHC, then it can use the magnet, the L3 magnet, and the ALICE TPC to search for particles. Of course, this necessitates to move the interaction point a bit further away from this, so that to allow long-lived particles to decay. So here we have, in this dark photon model that I mentioned earlier, the various reaches of the experiments. I don't have much time to go into details.
No, 2 minutes, 2 minutes.
Thank you. And there's no time to talk about this, so I will go to the milli-charged particles, the millican. It was the first experiment to propose such a thing. So already the demonstrator has run and has given results. There are 2 detectors for round 3, complementary, the bar detector and the slab detector, different types of scintillator bars and slabs. And here you can see how these projections of these different bar, the green and slabs in blue, they compare with the results already taken by the Millikan. And of course, this is the reach from medal. And the last but not least, the Formosa, this is also a milli-charge detector that is going to be installed in the future forward physics facility in the UJ12 hall. So it also is going to cover strongly interacting dark matter. In the case where the dark matter is interacts strongly with matter, and therefore it can escape detection from the direct detection experiments. And you see how it will cover this space. And this brings me to the outlook. So I hope I have persuaded you that there are several proposals for experiments to search for long-lived particles, also including the dark sector. They're well underway. So there's a different perspective, let's say, on the dark sector, and not only that, in the long lifetime, which is expected for LHC round 3 and beyond. Thank you for your attention.
Thank you very much for giving again the talk, this time recorder. I do apologize for the glitch. We had one question when you gave the talk about the order of the interactions of the strong interacting dark particles. Then you referred us to the reference. So with this, I would like to thank you very much. Now the connection will close. I apologize to the ICRANet for this extra delay. I would like to thank all the speakers again, and I will see you tomorrow. Thank you very much. Thank you. Bye-bye.